The scientific revolution starts now.
The DemystiCon podcast.
Let us see in the dark.
Very aligned with in both of your projects to try to visualize the inner structure of an atom. And we mean that both logically, we understand the logical connections that give rise to all the different attributes and connective attributes in an atom, but also geometrically. We want to know exactly what the internal geometric structure of an atom is. Now, I know that it's been in fashion for a while now to kind of abandon that approach as if it's impossible, but that's the audacious step we're moving is we're taking on a task that's been thought impossible for decades now, but we're also using tools that weren't available back when that opinion was formed. Major tools, Wolfram Alpha. So Wolfram Alpha is a tool that allows you to look for closed forms or mathematical connections to things that you may never find in one lifetime. You could ask questions and get answers to things that would have taken more than a lifetime to get. So it really accelerates the process. We didn't come to the things that we're going to be talking about in here from a starting intuition of what things must be. I spent years researching physics, reading about physics, keeping track of the different opinions, even though they're usually laid down as if this is what's thought. Different authors have different opinions and different intuitions about how those things make sense. And I tried to form my own model, and I couldn't go any further. I eventually got a better intuitive understanding of gravity from that model, but that model, as far as I could tell, couldn't be extended to give us any new insights in quantum mechanics. And ultimately, what we want is a picture, a logical construction of something that helps us understand all of the features that we are aware of so far, and maybe reveal other features that we haven't discovered. So I had to completely step back from that model and say, let's just organize and collect all the constants of nature, all the measurement data points that we have. And we're going to be going through some of it, but I want to preface it a bit to make sure you don't feel too intimidated when you see the list of constants that go data. It's a lot of puzzle pieces, and we're going to try to break down how you might go about trying to put them together. And I want to make it clear exactly how we're doing this so that if anyone disagrees and wants to come up with another way or start generating another model, you'll know exactly the process we're using and the tools we're using to participate in this process also. So I started here with what ChatGPT thinks the Physics Monastery looks like. I think it's a pretty cool picture. What? Yeah, they're working on a time machine. It looks like, huh? There's a big blackboard, so that's kind of right. But the atmosphere is pretty much like that. Not candles, and we're usually using laptops, but it's pretty much like that. We spend our day focused as much as possible. We wake up, eat breakfast, and then we're in conversation of these mysteries all day long. And we try not to be interrupted. I keep my phone under my pillow on silent. I don't check my emails all day. I don't go on Facebook or Twitter. So it took a long time to kind of get used to that. But the goal was born out of a slow realization. It took me a long time going through physics. I kind of always had this assumption that the super smart physicists out there in the world, like Ed Witten and all the big names that you come to really respect, that those guys are working on the fundamental, most important problems. I felt that had to be the case. And so I started reading all their papers and couldn't find them working on it, and reading more papers and couldn't find them working on it. And working in academia, I worked at NASA. I met a lot of brilliant people working on a lot of interesting things, but nobody working directly on trying to interpret the constants of nature. All of them, though, as far as I know, would agree that that's the central aim, the central thing that needs to happen for a revolution in physics. So we have constants of nature that put together the stories, the scripts we call equations in physics. They tell us the relationships built in. These are very hard earned, right? In a lot of cases, we had to build tools like CERN in order to get these measurements, in order to find out about these relationships. And keep in mind, this is a very abstract thing to begin with. All the constants of nature are things that no one sees directly, that the senses of just our body don't actually penetrate. We need to build tools that can help extend our vision and extend our, all of our senses to make sense of these different constants. So it starts out abstract. And from that, when I go to the theme on their car, learning to see in the dark, this really hits home for me because I feel like it's maybe a lost art to remember as adults now in the modern age, that when you were born, you couldn't see. you couldn't see what you see now. You didn't see the walls. You didn't recognize the room as it is. You've learned to see that, right? We've learned by interaction and touch and feel. And most importantly, by the mode, the conceptual mode that we've adopted. It's often hard to really appreciate the way we were taught to think because it can do so much for us, right? It's a historical treasure that we've all been handed. But the truth is that our bodies are being impinged by the environment all the time. And the number of things you can actually process compared to the number of inputs coming to your body is orders and orders and orders of magnitude less. So the processing where make sense of the world, we're only taking a fraction of a fraction of a fraction 10 times down of the actual data about the world. And we're getting used to always just taking that fraction and stringing together what the world is. So it makes you really, really uncomfortable to say we really know what the world is when we're all practicing together, telling each other what the world is. So the goal is to step back and remember that we don't really know most of these things and to remember how we come to a different conception of what the world is. So learning to see in the dark, I see as one of the major goals of science. One, to remind us all the time that we're kind of in the dark conceptually, and we learn to literally see, like sight is a projection of our imagination, right? And as our imagination takes in inputs, it weaves it together to tell you what the world is, right or wrong. Maybe we've always been wrong, but the goal of science is to try to hone in on the cues that are most relevant, the ones that are telling us the most important things so that we can, since we can't get past this limitation of only using a subtraction of the cues, to take the most important cues to tell us what the world actually is. So I'll start with some mood setting quotes that kind of go along with that. Einstein said, "Look into nature and then you will understand it better." To me, this is very important. He told this to his son after a death to try to understand the process of death and so on. But it goes further for me to think the things we should focus on if we're trying to make sense of the world, if we're trying to learn how to see more accurately what's really going on, are the cues we're getting from nature. And I'll go another step further and say not just the ones that we can pick up with our bodily senses, but with the experiments we can design to extend those senses, to look even further than we could naturally. Okay. Another famous quote by Roger Penrose, "Perhaps what we've mainly missed is some subtle change in perspective, something that we've all missed." This is a foundational essence of what science really is. I mean, if you're aware that you haven't got the whole picture, then it's obvious we've all missed some important cues. There's something else that we need to learn. And when we do, it'll shift us to a way of seeing that looks different. The environment we're looking at right now will look different to us. And this has happened many times throughout history. In fact, this is what we call the history of science. So I want to go through a couple of the important changes of science. And the very first birthplace that many would say, the grandfather of science, is it's always hard to say his name for me, Anaximander. And he's the grandfather of science because a few reasons. Most importantly of all, he was the first to use measurement in his investigations of the world. He was the first person to try to take something more systematic and use that to then tell him what the world was like. And he was also the first person that we know of that used the magical power of writing things down in his investigations of nature. So it could be that many other people in his time were making similar ideas, but they didn't write them down that we know of. And this tool of using writing is hard to understate how important it is. It's really hard to understand because our memories aren't that long. They're not that reliable. And it's very difficult to take a very large, complicated thing like the real world and pick up on cues about that world and keep them all in your head. You know, how many can we remember? 10, 50, 100, maybe? But it caps out pretty quickly. And there's very obviously far more to remember than any of us can hold in our head at one time. So learning to write things down extends what you can talk about, but it also lets you go back and analyze your thoughts, lets you review what you were thinking and why, and become more critical with your logic. So he's the grandfather of science. And anybody know what kind of measurements he invented? Yeah, like, yeah, measurements of distance and the first measurements of time. So he's the person responsible for inventing maps. That's a very big deal and a very central part of our worldview now, right? Now that we're all used to Google Maps and everything, we're regularly referring to maps and imagining how the map is not the territory, but it's conveying information about the territory. And that information is supposed to be geometrically representative. It's smaller in scale, of course, but the angles are conserved, and it tells you real information about the thing you're trying to encode. He also invented the gnomon, or the early version of the sundial. It's basically just a stick standing up, and the shadow of the sun cast to a certain point, and over time that shadow moves. The sun moves and the shadow moves. And you can measure the length change in the shadow to get a measurement of how much time has passed. Okay? Time has been historically incredibly difficult to measure, right? I mean, we'll get, actually, I don't think I included that. The ability to measure time down to a second accurately at one point was worth what's equivalent to millions of dollars today. And the prize money was out for that. Because when you're sailing across the world and you don't have a clock, you don't have an accurate chronometer, then your ability to be confident about where you are in the middle of the ocean is limited to your ability to know what time it is. You can know how far north and south you are by measuring with the sextant the position of the North Star if you're in the northern half of the planet. But how far east and west you are really requires having a clock. You have to know more than just a clock. You have to have some maps, some star charts that tell you, say, if you came from England and you're west of England, you need to know what time, say, the sun sets in England that day. And it changes throughout the year. So you need to have the list of today, England sets at sunset at this time, or this specific star sets at this certain time. And now you measure the height to the star, or you measure what time the sun sets from where you are. And that difference in time will tell you how far you've moved west. Okay, so getting your west position is much more complicated, your east-west position, much more complicated than north and south. But these things all come from measurements, and they relate to you where on the world you are. Galileo Galilei, called the father of science, is called that because he then took measurement to a whole new level. He decided to, and this is a remarkable thing to imagine, before him, nobody measured gravity. We've all had developed, every human before him had developed an intuitive understanding of what gravity is, a way to interact with gravity. If you're shooting an arrow, you have to get familiar with how high and so on. How strong gravity is depends or affects everything you can do in the field of gravity. But no one had come to the idea that they could try to understand gravity to a new level by meticulously measuring how long it takes something to actually drop a certain distance, measuring the distance, measuring the time, put it on a ramp to slow it down and get tick marks and get more and more resolution for this thing we call gravity. So he didn't invent the telescope, but he was, as far as we know, the first person to think about pointing the telescope up at the stars and using the spyglass to get a bigger resolution of the sky. Now, historically, it's kind of fun to remember this. Most of the people he showed this telescope, when you looked at the Galilean moons, they would look in the telescope and report seeing nothing. It was incoherent. It didn't make sense. Didn't see what he was talking about. It was just nothing interesting. A few people could transcend to a mindset where they had some sort of expectation to what to be looking for, and then they would see the moons around Galileo. This is a really interesting or poignant thing to remind ourselves that if you don't have a conceptual framework for what you're looking for what you're trying to see, you can't see it. The framework itself is what allows your vision to allow your brain to see what you're seeing. I had an example with that. You can see Jupiter during the day on a clear day, right? If the Jupiter's up from your point of view and there's no clouds in the way and it's not near the sun, then on a clear day, you can stare up at the sky and wait for your eyes to adjust and adjust and adjust. And if you know what to look for, it'll eventually show up. Okay, it'll be a small little star-looking thing. Now, if you've seen pictures of Jupiter online, and that's your only reference to Jupiter, is this big ball with the colored bands on it, right, and a bright eye, and you're staring and you're looking for that, and that's what you have in your mind that you should be seeing. You keep looking for it and keep looking for it. You never see anything. It never comes to mind. You can't ever identify where Jupiter is. And I tried this with several people in the past, and I didn't ask them ahead of time what they thought Jupiter was supposed to look like. I just told them you could see Jupiter and have them try to find it. And those who were, afterwards I would find out, those who were expecting to see a star-like looking thing would find it, often faster than me because my eyes aren't the best. But those who were expecting something else never saw anything and would be confused and irritated by this. Okay, some of the transitions of thought that we had of using tools to look further. So this is a Foucault pendulum, right? Very simple tool. You just hang a weight from a height and then swing the weight. Now the weight's just going to go back and forth in the same direction, covering the same path on the ground, unless the wind's blowing on it or there's something that's going to alter the path, okay? Well, we really wanted to know in the early times whether the Earth was moving, rotating about its axis, explaining the visual that we see that the stars go from east to west every day, or whether the Earth is holding still and the stars were moving. And this tool right here was the deciding factor. Let's see, what would we see in each case? If Earth is holding still, we put a pendulum up on the North Pole, and it's going to be swinging it back and forth on its axis, and the stars are moving, then when you look at the paths the pendulum goes down by the ground, it's always over the same path, back and forth, back and forth. But when you look up at the sky over time, it's pointing towards a certain star now, and then several times later, when the stars have rotated, it's now pointing at a different star. So the pendulum is aligning over time differently with the stars, but staying fixed in alignment with the ground. That's if the stars are moving. If the ground is moving, if the Earth is spinning and the stars are holding still, then what do we see? Now we'll see the path of the pendulum stays fixed with the stars. It always points towards the same star, but it changes its angle on the ground. Does everybody see the difference here? So the pendulum is in both cases staying fixed. We're not invoking wind or anything to change it, and you put it in a chamber to block the wind if you want to make it more accurate. But the difference you see is stark here, right? At least over time. You watch, in fact, many people have probably seen this now in different observatories, or right? You have these things all over the world now to show this experiment, because it only takes about 4 minutes for this thing to move over to the next domino and knock it over, right? So the world spinning is going to make the pendulum look like it's changing its angle, not look like, it changes the angle on the ground. But if you could extend and look out the plane of the pendulum swing, it would always be locked with the same set of stars. All right, of course, we all know now what the answer of this is, but it's really nice to remind us how we came to that conclusion conceptually. Another mood-setting quote: "All the great empires of the future will be empires of the mind," by Winston Churchill. This is kind of in setting with what I'm imagining here. The science is carrying us from one mindset to another mindset. And we might go down dead ends. We might make wrong moves as we change mindsets and have to back up and rely on other things to be cues to go to another mindset. But right now, in physics, we've been stuck in our mindset for about 50 years, okay? This isn't to put any specific physicist down. We haven't come up with an insight that carries us to a mindset that makes better sense of the data points we've been collecting. So that's what I mean by stuck. We have made improvements. We figured out the quarks have mass. We have a few different small things, but nothing that completely revolutionizes the way we tell the story about the world and how we see the world around us. So Edwin Abbott wrote a fantastic small 100-page book, and I hope everyone here has already read, called Flatland. And in this book, he makes points about the oligarchy. He makes societal claims and so on, but he wraps a story together in which the world that he's talking about, or the creatures he's talking about, are two-dimensional beings. And they're faced with a mystery from a higher dimensional setting that they can't make sense of. And here's a frame, 1, 2, 3, 4. So the first one's the first frame. A flatlander might see this little orange line to the right. And then as the next time they see the orange line has widened and moved a little bit to the left. And the next moment, it's gone further to the left. And then in the next moment, it's gotten shorter, but also turned green. And the flatlander then just sees this whole thing disappear. It came from nowhere and it disappeared in nowhere. But for some reason, it changed its shape and its position and its color, and then it's gone. Making sense of that can be incredibly difficult if you're stuck in a two-dimensional worldview, right? That's the data set. That's what you saw. That's what you report. And now you have to come up with a way to make sense of what that thing really was. Of course, if you go to a higher dimensional perspective, it can be really easy, right? Feel like it doesn't take any work, at least at the stage or the mindset we have about what the world is right now. It's a very common, familiar kind of thing. This is just carrot falling through the plane of view of the Flatlander. Another way to look at this would be a statistical way. If the Flatlander was looking out in the horizon and just seeing a flash of a certain color, and then a flash on a different place on the horizon, a different color over and over and over, that thing would be incredibly difficult to model. You'd have a statistical model of how often these things happen, how regularly they occur, how likely it is to see one color versus another, maybe, but you're not going to be able, no matter how you statistically model this, you're not going to be able to predict exactly when and where and what color the next flash will be. You're just absent of that ability if you're missing degrees of freedom of the story. So when you go to the richer view and you're looking at a pool table now, and you see the line across the pool table that you were looking, now as things are bouncing around, you can come up with a way of modeling the system that allows you to well in advance predict when a certain color will cross the line and where. Okay, so higher dimensional perspectives or additional dimensions or additional, I'll leave it at that, can really change the way that you're making sense of the observations. Plato said, "The true lover of knowledge naturally strives for truth, and it is not content with common opinion, but soars with undimmed and unwearied passion till he grasps the essential nature of things." Plato's a particular hero in history for me also. I imagine for many. He's very famously known for the Platonic solids. Okay, and the Platonic solids for me aren't just interesting shapes in geometry. They're interesting for a reason. They subdivide the sphere equally. If you're trying to tile something, therefore, in a way that doesn't extend out to infinity, but eventually wraps back on itself, so the same process or one or two steps can be done over and over and over in order to just continuously go, then these shapes play very important limiting roles for how those things must be done. So there's many other things, of course, Plato's known for, but this one stands out for me. All right. Early on, we didn't just think that maybe the stars were rotating around the Earth. We also thought that Earth was flat. All right. Very difficult thing to see. If you haven't traveled very far, this is the first guess perspective you might have, right? Of course, there's mountains. I'm not saying it's exactly flat, but if you model the world in your mind, it extends to the reaches of what you know of, right? As far as you've gone. And whenever you look out at the horizon, it pretty much looks flat. If you've ever been in the ocean, it looks really flat. The horizon looks exactly the same everywhere. If there's no clouds in the sky, it looks absolutely flat. In fact, let me tell a little story. I was in the middle of the ocean on a small 52-foot sloop. And in the middle of the night, if it's completely clear, which it mostly is, at least all the time I was crossing the ocean, at nighttime it gets really clear. And the stars get really, really, really bright, right? If you get away from light pollution near cities, then you can see the stars much more brightly than you can near cities. And when you're away from bright lights for a long time, 20 minutes or so, your eyes adapt to the darkness. So you can also, for that reason, see the stars to a much greater degree. The surprising thing for me, I hadn't expected this ahead of time, is that at nighttime, the stars are really, really bright above you, but below you, they're reflected, right? The ocean is often very calm at night. You're just barely moving along. And you can see stars below and stars above. It feels like you're floating in space, right? When you look around the boat, it feels like your boat is just floating in space. Now, our propeller was a fixed prop propeller, so it was spinning as we were being dragged forward, churning up the water a little bit. And there's throughout the whole central area of the ocean, it's warm enough to permanently have plankton. So whenever you mix oxygen into the water, it excites the plankton and they light up. They make a little green light for a short amount of time and then fade away. But our propeller had 3 prongs. And so behind us, if you look off the back of the boat, behind us, there's 3 streamers artistically following behind the boat, fading off in the distance. So it didn't just look like we were floating in space, 360 stars everywhere around, but there was a magical propeller of these 3 reaching out green arms that were extending us out in space. It was a really gorgeous thing to experience. If you ever get to, that's worth all the journey just alone, in my opinion. All right, so we had this perspective that the world, as far as we've seen, was flat. And people back then seriously debated. Sailors that wanted to go out had fears of traveling too far in the ocean, right? A genuine, deep-reaching fear. It wasn't a fear of a whale coming and swallowing the ship. That's a fear of monsters, sure. But if your model of reality is this, then the ocean surely, eventually, is just a waterfall. It falls off the edge. And if you're a ship that doesn't have a very powerful engine, because everything was man-controlled, right? Man-powered or wind-powered, then you're probably just going to get sucked right off the end of that waterfall. If you get close enough to see it, your end is probably already sealed. Okay, so the idea of exploring out past where you've been came with a sense of terror when we had a model of the world that was like this. It was naturally terrifying to even extend yourself to see what was past what you already knew. Then, of course, we changed to a spherical, a bladed sphere picture of the world. Took a long time to get there, but early on, we had this different model of the heavens. The stars are now out at some celestial sphere distance, this further outreaching spot. And you can think of it like a spaghetti strainer, where there's some reason light falling through. And this is the level of the heavens where we just got a whole bunch of dots of light. But there's 2 important things that everyone notices right away: the sun and the moon. They're up there, but they don't follow the same set of rules, it seems, as the stars, right? First of all, the sun looks drastically brighter than the stars. And second of all, the moon and the sun follow different paths than the stars, right? They're always changing where they are compared to the stars. Now, today it might be less common for people to be familiar with the map of the stars, right? To be looking outside and to recognize different constellations by name and association and have a whole story put together how this constellation relates to the next one and so on. That was extremely more common in the past, okay? Very common for people to have. And around the world, they had different stories, but almost always they picked the same sets of stars to represent a constellation in that story. It's kind of phenomenal. All the way down to South America and Europe, we had the same, as far as I know, the same exact set. There's 88 constellations of stars, and they played different roles. They were made of different animals, but they told stories about these because the stars related to you the map of the universe you were in, right? They gave you reference for where they were, and they told you how to navigate at night. Literally, you could find how to get somewhere at night by referencing the stars and getting used to where they were. So this is a common thing that we might have lost. It's a delightful thing to practice. I think in an age where we just put in a position on Google Maps and go there just following directions and never really import the map in our head about where we're going or what kind of landscape we traverse through. It's maybe a bit of a lost art, but this art I would like to throw out is delightful as you learn to use a paper map and understand where you're traversing and keep the different positions and relative positions in your mind. The way you think about the world extends, right? You start remembering the distance between here and there. You remember the things, the landscape, the prominent features between. And now those things live in your mind, even if you never go back to the place. They're part of the world and part of the story of how that world extends. All right, so this first level of heaven, 3-level of heavens model, where we have the moon on its own level, on its own sphere. Imagine the spheres go all the way around and it traverses around the sphere. And the sun lives on a different level further out, and the stars are the furthest out. This is the model that they had back when the Bible was written. In fact, it's referenced in the Bible several times, right? The 3 levels of heaven. To notice what you need to notice to transcend to the next level, you need to be familiar with the stars. It's very difficult to do this otherwise. Someone could point it out to you, but it wouldn't really make the same impact. If you become familiar with the constellations, they're stories in your mind that relate to each other, and they belong in certain positions, therefore. But then you see one of the stars in that story change to a different position. It's kind of a big deal. It's a big deal. It's like saying that, your favorite hometown, I'm from Salt Lake City, it's like feeling like Salt Lake City picked up and moved over on the other side of some other state, right? Your world just rearranged itself. Okay, so when this was noticed, these things were first called gods, right? Because they're up in the heavens, first of all. But clearly, anything that's moving to a different position must be doing this by its own volition. So it's a god. It can move in the heavens. It has its own level of the heavens that it needs to be occupying. So when we first saw the planets, this is the model we moved to. The planet, in fact, means wanderer, right? So it's all these planets are named after gods that are wandering, and they wander in usually a fairly predictable path. Once you start noticing where they're moving, you can predict where they're going to be, the next night and the next night and so on. But there are exceptions. Mars will follow a path that then circles back like this and then keeps going. Seems absolutely baffling and weird. Why would it do that, right? So it's maybe a particular god you want to call it. It has different cycles with it. Many different groups of people had different stories to explain what was going on there. But the point is that those bits of information, those special stars, they still look like stars. Mars might look orange, right? And if you have really good eyes, sometimes when it's specifically close, you might see a little bit of diameter to it. But in general, they all look like stars. Like Jupiter looks like a star to the naked eye. To a set of binoculars, even, you can start to see the diameter. But to the naked eye, it just looks like a star, but a wandering one. Another thing is that these planets are different than stars in another way. When you look at the stars near the horizon, they twinkle, right? They're always twinkling. They twinkle more today than they did in the past because we have more pollution in the atmosphere, but they still twinkle. And the reason they twinkle, we know now, is that they're so far away that literally a photon or two at a time is coming from that star and hitting your eye. So the atmosphere has a pretty good chance of having something that blocks some and then lets other ones through, but not all of them get through. So it's an interrupted signal. And when you get up high and you're looking through way less atmosphere, right? The atmosphere's got a layer to it. If you're down low, you're cutting through a lot of that layer. You get a lot of atmosphere that has a chance to block that photon from your eye. But when you get high, way less atmosphere. So the stars all twinkle less when they're up high. But the planets still never twinkle. When the planets are down by the horizon, they still don't twinkle. So they have some special character, something you might ascribe to a god. They can do things even different than the stars can do. All right, how Isaac Newton had interesting character of history, right? It gave us binomial theorem and calculus. And fair to say we wouldn't have modern computers if nobody had ever come up with the ideas that he had had. Other people did, in fact. But if we still hadn't discovered those things, we would be in a very different world than we are right now, technologically. He said, no great discovery was ever made without a bold guess. I think this is really in the spirit of doing science. You don't know what you're doing is right ahead of time. You couldn't possibly. And if you do, you're not doing anything interesting. Right? The idea is to try to gather the information, try to decide which ones are most relevant, because there's no way you're going to get every cue at once. Try to come up with an idea of selecting the relevant cues and then put together a model to make sense of them. But to do that, you have to make bold guesses. And when we quench or when we stifle people from doing this, when we try to remove or dampen the curiosity or the personality that it takes to try to be making guesses and hopefully more and more guesses and going further and further, not just take your first guess and run with it and think that you're right, but practice making guesses. I think you were mentioning yesterday, you're going to do this for your astronomy class. You're going to have your students try to come up with a model that could explain the things they're trying to explain. I think that's a fantastic practice. In fact, the central core of science. And if we had more people doing that today, not that we don't have any, but we don't, in the field of physics, we don't actively encourage this process. Maybe because no one has a guess of how to do it and they couldn't do it themselves. It's not exactly clear. We heard a whole history of the charlatan of science earlier yesterday. I totally agree with that. He derailed us in a lot of ways by trying to get people to think that what science is no longer trying to make sense of the mysteries. It's embracing the fact that it can't be made sense of. I totally disagree with that opinion. I think our job as conscious entities are to try to understand the environment we're in more and more. And the more we do, the more powerful our consciousness becomes. The more we can do with the environment, the more we can modify it to do the things we want and so on. So Isaac Newton had a fantastic way of simply exposing some of the big, deep mysteries about the reality we were seeing currently. Now, this is a bucket of water. We've cut away most of the bucket, okay, to explain, and the water's holding still. The way he described this is he hung a bucket from a tree, okay, and wound it up, and then let it hold still for a while till the water was all smooth on the surface. So you got a flat surface. And then he let go of the bucket. And when you let go of the bucket, the walls start to spin. It starts to fall because the rope's untwisting, right? It starts to go down a little bit, but the walls are starting now to spin faster. And at first, the water's not spinning, but the friction from the walls gets translated into the water from the edges and spins. But you see the most characteristic feature here is that the surface takes on a non-flat shape. It climbs up the walls. It has a concave geometric description now. It's completely different. So if you were to see this and this without the arrow, you should be able to tell which one's spinning and which one's not. Okay? The question, though, that he was trying to drive home about this is there are properties of spinning. Spinning is a type of acceleration, right? An acceleration is like a step past velocity, which is a step past position in time. The elements that make up acceleration are units of length and units of time, right? So here's the weird thing. Time is a relational thing. As far as we can tell, it's entirely relational. You know, what time is it? It depends on what standard we all use as clocks that we agree on, but compared to what is the thing you always have to answer if you're answering what time it is. What position is this thing at? Compared to what? Where's the zero of the reference frame? Without that information, you're not really conveying anything to anybody, right? So position and time themselves, the notion of position and time are completely relational. Not sometimes, all the time, as far as we know. If you divide the position in time, right, a change in position over a change in time, you get a velocity, which is also a purely relational measure, right? If you want to mention how fast something's going, compared to what? It doesn't mean anything until you've finished that bit of the information. But strangely, when you divide velocity by time one more time, you get acceleration. And acceleration doesn't look relational. Let me try to make clear. It's a subtle, hard thing to get at first, but let me try to see. If acceleration were relational, you should be able to spin yourself around this bucket and it would look flat to you while I'm standing at the side, not spinning compared to the bucket, but I see this bucket spinning and I see the concave walls, right? We should see completely different things. Now, I don't know if you've ever put a bucket in the middle of a merry-go-round and started spinning it and see the walls climb, then jump on the merry-go-round to see if it looks like they're still flat. But if you do, they don't. The walls still look like they're going up. The concave shape is still completely visible if you're on the merry-go-round or if you're off the merry-go-round. Why? This is baffling. If acceleration, spinning is a form of acceleration, is made of completely relational components, how did they get this non-relational essence? This is, I think, a fascinating thing. He used just a bucket of water to expose some sort of glitch in the way we're thinking about the world. Now, Mach saw that it was all purely relational, and you had to compare it ultimately to the background stars, right? So in Mach's view, the only way to make these things work out was to say that you're in a hypothetical universe that has no comparison. There's no stars or anything in it. As long as there's some stars to compare, then this will make sense. And Einstein originally was on that side of that view. In fact, he wanted to prove that view and ended up taking us to a different whole perspective where space and time were married together. But the end result of that was that he had a zero field of space-time, a field that wasn't warped, and that was the ultimate reference for acceleration. So in the end, he ended up finding a reference frame that made sense of the non-relational properties of acceleration. It's a really interesting thing that you can expose the mystery there with something so simple to me. Another thing I just wanted to throw in here, if instead of water, we put a superfluid, so a supercooled liquid helium in the bucket, then we wouldn't see the same thing. In fact, what we see then as we spin the bucket, all the rotational motion would turn into little vortices. We'd translate it into little vortices inside the bucket. The faster you spin, the more the vortices you get, and they even themselves out. But it's a completely different story there if we have a superfluid. Okay. Is that just friction? So it's because of the lack of internal friction. So it can't convey it the same way. Yeah. All right. Another quote by Albert Einstein, one cannot help but be in awe when one contemplates the mysteries of eternity, of life, of the marvelous structure of reality. I hope, and I get the sense that everybody here has some personal connection with this sentiment, that we all have noticed that there's aspects of the world that are ultimately baffling and exciting, and trying to make sense of them can be daunting, but can also be incredibly thrilling. John Dewey said, "Every great advance in science has issued from a new audacity of imagination." This is central to what I'm trying to make theme today. The audacity to extend your imagination and then maybe decide you were wrong and extend it another way and decide you were wrong, but to investigate a new possibility and find a reason that it's wrong, or find a reason that that new imagination allows you to extend to something you hadn't tried before, new things to test and so on. It might extend further, many, many steps before you find out it doesn't do everything you wanted. This audacity of imagination is practice of science. It's the attempt to try to make sense of more of the world. Einstein did this when he tried to understand how it is that, inertial frames. He used an elevator for this, where we can have a rocket in space, okay? If you have a rocket that's firing, so it's accelerating linearly, going in one direction, then if you're inside the rocket and you drop something, let's say you're accelerating at 1g, you're inside the rocket and you have no windows and you drop a rock, it'll fall at the same speed as if you were on the surface of the Earth and you dropped a rock. Both go straight down from your point of view. He wanted to find out why this is. How could this be the same thing in both cases? They feel like completely different situations, right? This is his audacity was to investigate these things, which felt like completely different things, and explain how they actually relate. I had a personal experience with this elevator thought experiment down at Doran, Peru. I was on a mining expedition, and it was at the time the most active and prolific mine on the planet for copper, gold, zinc, and lead, and iron. Mostly copper, but they were putting out the most of almost all of those. And they were very well organized. It was a really mind opener for me. But we got in this elevator shaft after being exposed to all the process of breaking up the rocks and mixing them with soaps to separate things and so on. We get an elevator shaft that was very rickety. It's not like the elevators in hotels now. It's just a crate, basically. And the shaft goes straight down, and it has a railroad tie going straight down it too. One, the railroad tie, not two. And there's a mechanism that locks onto the railroad tie, and it has brakes. Well, it wasn't all explained to us, or maybe it was, and I didn't understand the Spanish. But we all crowded into this elevator with a bunch of the Peruvians who were about this tall on average, and they were wearing hard hats, Speedos, and water boots up to their knees, okay? And all of us were wearing jeans and steel-toed boots and hard hats with lights on them, but long close shirts and everything, and gloves. So when we all crowd in, we were packed completely, as many people as they could put in there, okay? And all the miners were looking down at their feet, okay? And all of us that were doing this for the first time were kind of looking around at each other. But the guy who started the elevator, he pulled a panel off the wall, had 3 buttons. He pushed one button, and it just dropped us. Yeah. Just dropped. I didn't know this was about to happen. I thought that it'd be like a regular elevator. It dropped us. So instantly, if you just twitched your feet like that, you would float and hit your head on the sock. It's quite an unnerving feeling. We didn't expect that. I would have screamed. I would have screamed, but I looked around, and none of the miners who had clearly done this many times before were doing anything but still looking at their feet. Okay, this is completely normal to them. So as we're dropping, the mine cuts through rock and then eventually gets lower and cuts through rock, and it's usually 40 feet or so between levels. Well, so it would go inside the rock, and there's no more light. There's a light bulb at the level it's exposed. And then as we go through 40 feet lower, there's another single light bulb. So you'd see this light fast, and then a faster one, and a faster one. And pretty soon it's just a strobe light. You guys have seen strobe lights where people look, it looked like that. And I thought, of course, after about 2 or 3 seconds at this dropping speed, he'd be pushing another button that would make us start to slow down. And he didn't. We just kept dropping and kept dropping. And now, if you know the acceleration equation for 1/2 gt squared, you can figure out every second you're falling faster than the second before, right? And it's really getting more and more and more. And of course, you get verification of this when you see the strobe light. At some point, you can't tell the strobes anymore. It looks like a solid beam. of light. And even though there's 40 feet between each flash, okay, we're going really, really, really fast. We were also making a wave front in front of us where we take our cold air that's inside of the chamber and we're keeping it, but we're buffeting air around us. When he finally did hit the brakes, before that, I was working my way to the edge. I started out in the middle of the chamber and tried to work my way to the edge, thinking that when we hit the bottom and we all about to die, maybe if I'm at the edge, I can fall on top of everybody and save something. So when he finally stops, it starts stopping really fast. Like if we weren't all packed in, we would have fallen down, most of us, but we were packed in like sardines. And when the thing came to the bottom and stopped, the first thing I thought was that, something's terribly wrong. I think I broke a rib. Don't know how, but I think I just broke a rib because I had searing pain inside here. That's the only thing I could think of right away. Somehow I just broke a rib. I didn't get hit by anything, but somehow my rib just broke. And then I tried to breathe again. My second breath, it burned. I noticed it was really burning. The first time I didn't interpret what was happening, but I immediately tried to cover my mouth and breathe through my fingers and sucking air through the crack of my fingers. It was burning my fingers. It was so hot down there. Now, these guys are a lot shorter and they have very wide lungs, and they all had practiced how to breathe in superheat. I don't know if you ever opened the onion or the oven too quick and then breathed in at that time by accident. If you breathe that hot air, it sears, it hurts, right? It was down, there's no way to escape it though. So we were all trying to put our shirts up, breathe through our shirts and our fingers. I had gloves on, by the way, and it was burning my fingers. It was really hot down there. So eventually I was about to panic. I was actually starting to panic. The problem is you just can't breathe like a panicking person. So I had to look around and see how were the short miners doing this. And they were breathing extremely slow. Breathe in real slow and breathe out real slow. So I started copying that and eventually was able to do that. The problem is you can't now do something that requires exercise. You can't pick up your rock hammer and start working hard because you naturally start breathing faster and require more oxygen, and then it starts burning you again. So they got used to the slow pace, really slow pace. We would follow them. We'd have to go through a boiling river. It really felt boiling to me. It was burning my legs through my jeans, going about up to the knees and then cross up to a dry spot again. Eventually, I really wanted to dig some of the pyrite out of the roof, out of the ceiling. It's bad etiquette to do that in a cave. And I'd had a lot of practice in caves, so I was pretty confident I could dig this pyrite crystal out. And it was one of the biggest ones I'd ever seen. So I really wanted this pyrite crystal leaching out of the rock. I think we were about 1.5 miles down in this Doran Peru mine. And I waited until everyone left in the tunnels from my point of view, and I started trying to dig this. And some guy starts yelling at me. I didn't know where he came from. He's yelling at me in Spanish. I had no idea what he was saying, but I knew exactly what he was saying. So I was now, deterred from getting my little treasure there and also exhausted. So I needed to sit down. There was a pile of loose rocks right there. So I sat down on the rocks, just to kind of catch my breath and try to get breathing slow again. A few seconds later, I jumped up and left permanent holes through my pants and my underwear about that big. It burned through my jeans, just the rocks on the ground. That's how hot it was down there. Ridiculously hot. Anyway, this was an elevator story. So the state we were first in when we were first dropping was near zero gravity. Not exact. There was a little bit of friction somewhere, but it was really close. I mean, you can also reproduce this by flying a plane and you're pulling up and then tipping the nose just right and matching so that everything floats. In fact, I used to practice this when I was getting my pilot's license. You'd put something soft, learned that the first time. I had my big books of chemistry and flying books, which are always usually pretty thick, in the back seat. And first time I did a zero gravity, it flew up about right here. And then I pulled up and hit me right in the back of the head. So from then on, I make sure that bag had a seat belt and would bring something soft to float, because visually you can practice your technique really well if you put something like a teddy bear up on the dash and you make the teddy bear float and then you have it move around the room. And you kind of practice with the zero gravity. But the feeling, the sensation of zero gravity is a really interesting thing to get used to. If your only experience is, say, going up and driving and you go over a hill and you get a quick sense, at first you feel like this butterfly happening. But the butterfly thing is happening while you're changing gravity, when you're going from 1G towards 0G or less. Okay, the change is the butterfly feeling. When you're stuck at 0G, the butterfly feeling is not there anymore. You're just floating. It's a really cool experience. But the reference frame now is no longer accelerating, right? You're in a stationary reference frame, which maybe help remind us when we're on the surface of the Earth right now, we're in an accelerating reference frame, right? Here we are, we have weight. We can feel the ground resisting us, pushing back up on us. That's a state of acceleration. We often maybe conceive ourselves as being holding still when we're standing on the ground, but there's an acceleration that's part of the story there. All right, well, Einstein succeeded in wrestling through this mystery of trying to figure out these different inertial frames and figure out that these two things really were the same thing, except in this case, there's one difference. The shape of the gravitational field that you would assign to the rocket would be planar, flat, because we're assuming it's linearly traveling this way, okay? But the shape on the Earth isn't exactly planar. Locally, if you zoom way in on the scales we're used to, it's roughly planar. But ultimately, it's actually spherical or close to spherical. All right, so other than that, these things have the same exact characteristic. Einstein, again, is one of my favorites. I don't know if anyone's read my book, Einstein's Intuition, you'll see I really like to focus on the intuitive grasp he was reaching for and also seemed to have. He had a very powerful ability to intuitively understand the things that needed to be focused on and the things to wrestle with and make experiments for. So creating a new theory is not like destroying an old barn and erecting a skyscraper in its place. It is rather like climbing a mountain, gaining new and wider views, discovering unexpected connections between our starting point and its rich environment. But the point from which we started out still exists and can be seen, although it appears smaller and forms a tiny part of our broad view gained by the mastery of the obstacles on our adventurous way up. So Einstein saw the goal here, our model building of the world, not to destroy or tell people that they're wrong about what they currently think, but to get to a wider point of view that includes the things we've already discovered, but also includes the stuff that are considered mysteries right now. This is one of those mysteries we mentioned yesterday, the perihelion advancement of Mercury. Okay, one way to try to explain how that could happen is if there's Vulcan, right? A planet between the sun and Mercury tugging on it to make it change this like this. Another way, though, that ultimately we go today is that the sun itself in the middle is warping space-time with it. That warping is also a thing that we can assign energy or mass to. So there's an additional mass in the system that we were ignoring when we were just thinking of just the sun. The metric itself has an additional energy content. And that additional energy content acts just like another planet to give more tug to the planet. This, what became known as a warp sheet analogy for gravity, is a beautiful start. It gives us a picture, right? It gives us a way to try to imagine the force of gravity acting on a metric. But it also hobbles us in a way intuitively. And it's really interesting to point this out. So if we imagine we started with a trampoline and we put the sun has a certain mass and it bends the trampoline a certain amount, a thing to keep in mind is we're already evoking weight to pull down the sun and stretch the metric. We were trying to use this to explain mass and weight, not have it already in the picture. So there's something that unsatisfactory about that. Another thing is that we're taking just a slice of the picture, right? We're not doing the whole 3D, and we're imagining stretching just that slice. Now, you could have sliced it completely in a different direction and say the same sort of thing. But how do you imagine all the slices at the same time? Because in this picture, we're using the z dimension, the one that's not on the slice, for the stretching of the metric. Okay? So it's a reduced dimensional perspective that gives us a story to kind of understand the geometric effect we call gravity, but it still doesn't really do the whole thing for us. Mathematically, it's really easy to extend that picture into more dimensions and show that the equations work. But to have a full, rich picture that tells us intuitively exactly why all this is happening, we're partly there. We're not completely there. Now, I tried to work on this when I was model building. My approach was to think that if we can come up with a structure responsible for gravity that makes better sense of this, then hopefully that structure could be extended to make sense of quantum mechanical effects also. I failed, but what my attempt was to transition this to, here's our slice, and it has a whole bunch of different warps, undulations in it. To transition that slice into an understanding of, we zoom in on a slice and see it's actually broken up into different quanta, different pieces of space-time, okay? If this is the case, then you can actually make sense of gravity as a density field. If that's the case, all right? But notice this slice with the different density gradients in it, you can now immediately extend above and below. You don't have any restriction against that. So you can intuitively grasp this density gradient that we're blaming the effect of gravity on with no problem. The problem is that now you've invented a bunch of boundaries that have to have logical reason for their coherence. They have to be there for a reason. You have to explain them too. If you invent more things to explain the solution, you haven't really made progress, right? Unless, of course, you want to keep going further and you found a way that all those invented boundaries do something more to explain more of the picture. Mine didn't. I had a bunch of quanta, had a bunch of spherical balls bouncing off each other, giving us density gradients, which was great for making sense of the gravitational field in a richer way without having to reduce the dimensionality of it. But it didn't come with any obvious ways, and I spent years trying to find some obvious ways to extend into the features of quantum mechanics. So at this point, I needed to start over, right? Completely start over. I mean, I learned a lot of the features I need to make sense of, but my method for starting over was to, well, I'll get there in a second. First, I want to mention this atomic idea, this breaking things up into the world being made out of pieces, was early thought of by the Greeks, but rejected. Okay, they thought, well, if the world, the metric itself, is atomized, broken into a grid, then it would be like this. You'd have a 4 by 4 by 4 connection in things, which clearly can't happen because of Pythagoras' theorem, right? 4 squared plus 4 squared doesn't equal 4 squared. Right? So this was and Pythagoras' theorem was one of the most solidly believed things and held. So if you contradict in Pythagoras' theorem, you're contradicting very obvious evidence of things that we all agree on. Of course, there's a little catch here. When they gridded up the world, they assumed that the grid was all filled and there was no spacing between things and no reshuffling and reordering. Pretty good assumption, but how do you know? If you allow for things to be broken up and have the gaps, then you actually recover Pythagoras' theorem as you zoom out. If you zoomed in, it breaks it, but as you zoom out, you recover it. So Richard Feynman, another hero I expect for all of us, said, if in some cataclysm all of scientific knowledge were to be destroyed, and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is that all things are made of atoms. So this idea of making things of atoms, even maybe the metric, is a very powerful idea. It's, of course, the mainstream perspective we have now. All the material things we see around us are made out of atoms. That's the story we have, right? And the real goal is to understand the logic that maintains the structure in these atoms from atom to atom, the logic that holds one atom together and so on. But the fact that the world is made of atoms is something that we've clearly observed at this point. There's a lot more to make sense of, but that holds. The Casimir effect, for example, this was first proposed by Henry Casimir, maybe 30 years later was shown, and in between was really not expected to be true in any way. It was just a quirk of thought. But he said if you take two plates and we have things jittering around at all different modes, different wavelengths of jitters, well, between the plates, you're actually restricting some of the possible wavelengths. The velocities that things can have, the wavelengths that they fit, are cut off by the size of the spacing between the plates, between the sheets. So in that case, what should happen is you'll have a subsection of possible motions inside and the full set outside, which means you technically have more force on the outside than you have between the plates, and it should push the plates together. Now, this was observed. It's tricky to observe. You have to get things really, really, really close together before you actually pick it up, but it has been measured now. So it suggests that there's something even more to this possibility that the metric itself is made out of quantum bits. Another thing, we get to quantum mechanics. Now this is, I'm artistically made this up to try to say what you would expect to see. If you shine a laser light on a single slit and you have a plate behind it, you would expect to see, well, the light still spreads out, everything that goes through the slit, and you get a single line, right? This doesn't shatter anybody's intuition. It makes total sense. If you put two slits, you would expect to see two lines, right? You get light going through the right one and through the left, and they're just spreading out. And based on how far back you put the plate, and how determines how big and spaced apart they be. But all the light's just going to go through the slits and make two lines. Surprisingly, that's not what you see. This is what you see. There's an interference pattern. Now, what I mean by interference pattern is simple wave construction. If you imagine putting the slits halfway in the bathtub and making a distortion on one side of the bathtub, and those waves travel to the slits, then the waves, some of the wave goes through the left slit, some of it goes to the right slit, and those waves now are new wave fronts that then interfere with each other, and on the back end of the bathtub are going to have a profile that's highest in the middle for the brightest peak, and the next two, as you go left and right, get a little dimmer and a little dimmer and so on. This is a classic wave interference pattern showing up from things that we may have thought were photons, right? Single little concentrated particles. More surprisingly is when you tune the laser down so that it only has one photon at a time, or electron. You can do this with an electron gun also. I think in this case I meant it to be electron gun, but you can fire a single electron at this plate, and the ones that make it through the left slit or the right slit will hit the back screen on this characteristic pattern still. You might have really expected, I think most of us would have expected, that when you do one photon at a time, then there's no longer going to be this wave interference pattern. But what we found is the wave interference pattern still holds. So this particle-wave duality is built in somehow, not just to photons, but to matter. And this brings a central mystery about the world we think we're in, right? Quantum mechanics, everybody famously has no intuitive grasp of these properties. And that's really the goal we're after. We're trying to understand the structure that can explain all these actual observations in not just a mathematical, impenetrable way, but in a way that allows us to actually model, get a picture, get a geometry, understand the logic. If we have a genuine picture of an atom or a molecule or a lattice of molecules, if we had the full geometric picture, you should be able to give it to a high schooler and have them examine it and have them discover properties that this thing should have, real properties that it actually has from the picture. So we're not there yet. Right? We're making progress in science, but we haven't got to that point. And it's a very specific thing that we're looking for, the understanding of the actual features we believe reality is made out of. Galileo said that philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth. This is the learning to see in the dark thing here, right? If you don't have the elements of the language to build, if you're not talking in the elemental structure of properties that make atoms, then you're not going to be talking in the language of nature. And in Galileo's opinion, geometry is that language. So I know we all have a fear of mathematics. Mathematics is a strange thing that all of it that you know is easy, and all of it that you don't know is impossibly hard. It's got a really big intimidation wall for it. But as we practice, have an audacity, practicing that is try to practice tackling some mathematical concepts that you think are hard. You don't get any of them usually right away, but over practice and application, it starts to sink in. And eventually the things you thought were hard are in that pile of things that are just obvious and easy. And you move up to the next things that seem impossibly hard. But keep doing that is what I call faith. That's what it requires. You have to remember there is an answer we're chasing. There is one. The fact that none of us have found it yet has no bearing on whether or not there is one. There has to be one, right? There's too much structure around for it to be called random. There is a way to make sense of reality. And to find it, we need to use all the best tools we have. Galileo's cueing us in right from the beginning, the father of science, telling us that geometry is part of the language that we're trying to uncover. We're trying to learn to think in terms of geometry, to see the world that way. Here's an equation, very famous equation, perhaps the most famous equation for Einstein, right? E equals mc squared. Energy is directly equal to mass times by the speed of light squared. So C stands for the speed of light. This conversion, this connective equation is a perfect typical and short example of what we call a physics equation. It's a relationship built in, a relationship we've discovered by measuring things. Now, the speed of light is a magnification factor for the equation to make it fit. Okay, it comes squared, but the speed of light itself is a measured quantity. It's not a derived one. It's not a geometrically understood one. It's one we went into the world and have measured and better over time, but it's one that makes this equation work. That is a constant of nature. It's a relationship that nature has. When I say nature, this is built into the logic of matter. Atoms hold this for some reason, okay? And understanding why is the goal. But in the relationship here, I want to really keep your focus on the one that's called the constant of nature. This is the one that we're really interested in today. The E isn't so difficult. It's energy. The mass is mass. These are concepts that relate. If it was just E equals mass, then there would be not much content. But the fact that mass and energy are equal once you scale mass by the speed of light squared is a really intriguing thing. Somehow mass has a relationship to energy, and that relationship comes through the speed of light. Some more very famous equations. The force of gravity between two bodies. Mass 1, mass 2 divided by the distance between them squared, times by a scaling factor known as the gravitational constant, or Newton's gravitational constant. There's another constant we've measured, and this one's notoriously difficult to measure, so we have less significant digits for it, but it's a measured known. It was not derived. It's not known geometrically, right? It's a mystery. This feature of reality is a mystery, and the mystery all falls on G. Why is G the way it is? To hold this relationship. The fourth, electrostatic repulsion between two charged particles. You get charge 1, Q1, and charge 2, Q2, divided by R squared, times by Coulomb's constant, another constant of nature. These relationships are what we're interested in, right? But the relationships are made sense of and maintained by the constants. Now, every constant of nature has an equation like this. Every constant of nature relates to a relationship built into the logic of atomic structure. Understanding atomic structure is synonymous to understanding these constants, why those relationships are held. We're not there as a species. We haven't figured that out. That's the goal, right? So if the equations are mysterious, which they usually start out, what does that really mean? How do I get comfortable with that? Try to focus mostly on the magnification factors that keep these relationships true, that maintain them, the constants of nature. And here is the authority on the constants of nature. NIST, CODATA, keep a list, semi-active list. There's people making measurements all around the world, right, that update our best information, our significant digits known in the error bars for each constant of nature. And over time, they collect all of these and they put them all together to give us our best known measurement for each constant, the error bars, the units, and everything. So it looks pretty simple. Okay, you can look up a constant, or we can go to this all values and just get an idea. Now, don't be daunted by this. I know it's a lot of black and white. I just want you to pick up on, make this longer. Some of the names here. You got the alpha particle. There's angstrom star. Sorry, I didn't make the margins exactly right. Oh, I can move this over. Just a second.
Good.
Oh, which one? Top?
Good.
Cool. Thanks. Okay, I'm going to scroll down. You don't need to feel responsible to understand them all. Just get a little glimpse. If you've never seen these, each one of these are the puzzle pieces we're trying to make sense of. This is the raw data that describes the puzzle piece. They come with a string of digits. They come with a power. That little e to the negative something or positive something is times 10 to the, okay, it's shorthand for that. And the error bars, it tells you how far off. We know this number for this many digits, and then we have this size of error at the end. Okay, so it lists the error bars, it lists the dimensions that the thing is listed in, and the name. Or let's look real quick here at the fine structure constant. Okay, fine structure constant, 7.297,352,5693 times 10 to the negative 3. That means you start out 0.00, then 7,297, and so on. Okay, it's known quite accurately. Let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 significant digits. And the error is 11 in the last two. Okay? And it is dimensionless. Over here, there's no dimensions. Okay. Let's scroll real quick just to give you a look at all the rest of these things in here. Inverse meter Kelvin relationship. And there's a whole bunch of these things that are specifically relationships between the bases of the coherent units in the system of units. Okay? The constants of nature, the logic built into atoms, reveal very specific bases to support the equations that those atoms are maintaining their logic on. This is a big reveal in science, and I think most people are still missing this incredibly important point. When you think of the speed of light, you might think you can report it in feet per hour. And sure, that's going to give you a number and it relates in a way. But what you've reported isn't technically a constant of nature, because the constants of nature are relationships between the bases in the coherent system of units. It needs to be in that system of bases. So here, hopefully it becomes kind of obvious. We have the meter and the Kelvin. Those are two of the bases. And the inverse meter-Kelvin relationship is one of the constants of nature, right? You probably, as I scroll through here, you're going to see several of them. The bases being the second, the meter, the Kelvin, the Coulomb, and the kilogram. Okay, so this is a lot of puzzle pieces. If you're making a picture out of all this stuff, you need to eventually end up with a image that has all of these in it. That's the ultimate goal. This is what I would call it this stage from our current understanding of the theory of everything. Maybe in the future we'll discover more things that need to be included, but currently these are the hard-earned data points. And I know it's not exciting to see just black and white listed numbers, because let's be very honest, a string of digits and numbers means nothing to all of us, right? I expect. Maybe you've got a magically different mind where you just see a string of digits and it means something to you. When I see a string of digits, I have no comprehension of what they mean. And we're after a comprehension of what they mean. We're after some theoretical model, a geometric model, some logical constraints that give us these numbers with those bases. Why is it those bases? Right? Why are they so important to the constants of nature? Okay. So this website's incredibly important. They're behind on their latest update. So maybe with the next update, we'll get some even tweaked different numbers, which could help us even more, or we'll get some more significant digits in the sum. But with each stage, it gets more and more information there, more and more accurate information. So I singled out the fine structure constant for a couple of reasons. A lot of people are very confused, or should I say, uncomfortable with the bases in the constants, about how to make sense of that. Why does it need to be in meters? I should be able to put it in feet, and so on. The reason, of course, is because we have a coherent system of equations in physics. All those connecting equations, they're no longer true without another additional factor if you put them in other bases. Okay? So all the ones I showed you and many, many more, they have, other than the constant of nature in them, their scaling factors are all one. If you put them in other units, then you would have to add another scaling factor each time. So to minimize the information needed to explain all that set, we have revealed the set of bases that do that, the coherent set of bases. So here's a quote by Feynmann about the fine structure constant. He says, "There is a most profound and beautiful question associated with the observed coupling constant, E, the amplitude for a real electron to emit or absorb a real photon." This is the charge of the electron, E. Okay? It is a simple number that has been experimentally determined to be close to 0.08542455. My physicist friends won't recognize this number because they like to remember it as the inverse of its square, about 137.03597. Let me just make a note. Today's the eclipse, and the peak of the eclipse happens at 1:37. Here. Yeah, that's a cool coincidence. All right.
Auspicious.
Yeah. All right. So with about an uncertainty of about 2 in the last decimal place. This has been updated since then, but this is when he made the quote. "It has been a mystery ever since it was discovered, more than 50 years ago. And all good theoretical physicists put this number up on their wall and worry about it. Immediately, you would like to know where this number for a coupling comes from. Is it related to pi, or perhaps the base of natural logarithms? Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man." Now, this constant, this fine structure constant, can't be wished away because you don't like its units, okay? It's a central mystery in the constants of nature that's dimensionless, making it a geometric number like pi, except for we don't have the geometry it belongs to. Reality has another important level to access geometrically that we're completely at this point blind to, okay? Pi, if you've gotten familiar with pi, it's a very, very rich geometric number that gives us a lot of connections to many different geometric stories. This is another number like that, and it's a number that shows up in chemistry all over the place, in the constants in nature all over the place. If you take one constant and divide it by another constant, it'll show up many times that way. So this number is extremely important, as he points out. Yeah. Paul Dirac famously said in his office, people would come approach him and say, I've got this theory of everything I want you to check out. And he would just kind of look over his shoulder and say, does it explain the fine structure constant? Then come back when it does. I'm not interested at all unless you can explain that constant. So he was really focused on it. Now he's been called the strangest man, but he's also incredibly important for our modern formalism, right? And for the Dirac equation and so on. It's really important to focus or keep in mind if we're trying to make sense of the puzzles of reality, of the hard-earned data points of the structure we've discovered so far, which have all been gotten by extending ourselves past our natural senses, by using experiments, and the best experiments we can actually design so far, the best equipment we've designed. That's a central mystery to be made sense of. Now, it's, as I mentioned, found in many places in the constants of nature, but you can measure it using the quantum Hall effect or the anomalous magnetic moment of the electron. You can use atomic interferometry or the recoil measurement method. You can also use it from the atomic unit of velocity. There's many, many more on that. I think probably over 100. Okay, so there's many relationships that it indirectly comes from, but built in. Now, this is a bit of numerology. People have been fascinated to try to come up with a way to get close to that number, right? Anyway, because we don't have a method. So if you come up with anything that reproduces this number, we're interested to see what can I try to get from that? What sort of information might that be telling us? Now, I'm not telling you that this equation is anything more than a hodgepodge and put together of numbers, but I'm telling you it's kind of famous, called Euler's constant, for being able to get 5 of the significant digits right. It gets the first 5 parts of this number, and then it gets them wrong after that. Okay, but the first 5 numbers right, and that's really good compared to all the other attempts. Okay, it's been called a number in search of a theory. Okay, and of course we don't know if there's anything profound in there. When I look, I don't see anything particularly profound. Maybe I'm missing it. Maybe you can see it, but it is interesting that it gets us close to the number. Here's the reported number on CODATA right now. Okay, with the error bars, the last 2 9 digits, they have an error of plus or minus 11 on them. Okay, there's also other measurements. In fact, the more recent measurement from 2020, atop the second line here, and then there's several other ones that list the number and the error bars. So you can see this has been studied by many people. There's even more than this. These are some of the recent ones, people measuring these different. But in each case, notice that they have several digits they all agree on. Okay, so the error bars tell you where our ignorance is, but we certainly know this thing to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and with error on the last 2. So we have 9 confident digits and 2 not so confident digits, okay? Now we enter some of the work, finally, that we've come to. And I should say that I didn't come up with this equation out of my mind. Someone had someone read Einstein's intuition and knew I was after this sort of understanding, and they found a blog online where somebody had just noted that this equation, without the minus MP on the end, gets us really close to a solution, a number that's really close to the fine structure constant, closer than Euler's constant does. Okay, so I was immediately interested. And I reworked the equation. They had a different square root power of this and so on, but I rewrote it this way, which looks simpler to me. In fact, if you ignore the right-hand side and get rid of the 2 pi in the denominator, it's just an equation for hyperbola. Okay, a hyperbolic structure, and then we're dividing the volume element, the cubic element, by 2 pi. And I to the j, I is the square root of -1, and j is also square root of -1, but it's orthogonal to I, and then to the negative pi over 2. Without the Planck mass on the right-hand side, like I said, you get a number that's really close. I think you get 6 significant digits, 1 more than Euler's number. So I wanted to ask, what do you have to change this equation by to get it completely? To get all the digits we currently have? Of course, what you can easily do, you put a plus x on the right-hand side, and then plug in the actual number, plus y on the right-hand side, since we already have x's here. Plug in the actual number for x. And what it spit out was minus the Planck mass. Okay, the same power, 10 to the negative 8, the same few first digits that we have. And immediately I got excited. Okay, I think I just found a clue. I think I found a very important clue. First of all, this equation doesn't look like random hodgepodge to me. We're talking about a hyperbolic structure. It's got quaternion structure and has a gap in the quaternion structure of a certain scale. And the scale picked for the gap in hyperbolic structure, what we've been calling classically the mass gap, is exactly equal to the Planck mass. This was very, very exciting. More importantly, it took me a long time to notice all these features because I was after the fine structure constant. I wasn't necessarily after for all the other features it connects to because I didn't get that yet. But there's 4 solutions in this equation, not just one. So it kicks out 4 different solutions. Let's look at them right here. On the bottom, we have J1 is a solution. This is the number that Feynmann was talking about, the square root of what we currently call the fine structure constant, but he called the square root version the fine structure constant. And then J2 is another solution. If you put it in the equation, it kicks out an equality. J3 and 4 are 2 other solutions, and notice they're complex. They're 2-dimensional numbers, a real part and an imaginary part. Okay, all 4 of those solutions taken together as a product returns 2 pi. As a sum, when we add all 4 of those solutions to that hyperbolic construction together, we get 0. And when we take their quadrants, which is the sum of their squares or the difference of their squares, both count. If we take the sum of the squares, we get negative 4 pi. If we take the difference of the squares, we get positive 4 pi. Okay, that's another thing that made the hair stand up in the back of my neck. All of a sudden, we have a direct connection to things that we know much more about. In fact, this is now a partition structure relating to 2 pi and a projected sphere and a balance coming from a hyperbolic structure. A picture's starting to form here. All right? Another really interesting thing, the bottom left, J1 squared, is equal to the fine structure constant, to all of its digits currently known. Okay? And J1, the one that Feynman called the fine structure constant, the square root of that, times by the Planck charge gives us the electron charge. So it's the story we're after is a story for that, either fine structure constant or J1, however you want to call it. But all of a sudden, it's connecting to more than one thing, right? We're after one thing, the fine structure constant, but it's connecting to more than one already. All right, I need to talk a little bit about the 5 bases of the logic we found in matter. Time having a base of seconds. This, I imagine, is probably very difficult because everyone already has a familiarity with the word seconds, right? And it feels like a random man-made unit. But I really want to drive home that the unit that we use for seconds now in science, in physics, is a very specifically defined unit that we get from the constants of nature. We didn't come up with it. We found it from putting the logic of the puzzle pieces together in constants of nature and have defined the second using it. We've defined the meter using it. And our definition changes as we get more and more accurate measurements of the constants. So we get more and more specific information, another significant digit, say, for our definition of the meter and the second, and the coulomb, and the kilogram, and the Kelvin. So all 5 of those are bases in 5 different dimensions, okay? What I'm imagining now is we have an atomic structure that internally maintains itself by dividing into pieces, creating boundaries that all fit together. If you remember back when I said I was coming up with a model for intuitively understanding gravity, the problem for that model was that it had a bunch of boundaries that were separated, that didn't have a logic maintaining themselves. They were just kind of ad hoc thrown in order to make it so we had a picture. Well, here we're talking about a structure that's a manifold. A manifold is something that has boundaries, but all the boundaries connect. There's no gaps. There's no unexplained structure in there. The boundaries maintain themselves. The simplest possible manifold is known as the Guiskine manifold. And a double cover of it, so if you use the Guiskine manifold to cover itself and therefore maintain itself, you get what's known as the hyperbolic figure 8 knot. Now, this was made by Henry Segerman, or the STL file, and Vanessa Moon printed it out for us. I'm going to pass it around so you can kind of get a look at the inside. But this is a structure, it's a boundary that closes on itself. If you think of a flat sheet of paper, like a rectangle, it's a sheet that has boundaries, but those boundaries are all something you could walk off of, right? If you put the piece of paper down, you can go put an edge and you could jump off the boundary at each of the edges. If you roll the sheet up, and connect two of the opposing edges and tape them together. Now you've gotten rid of that boundary. If the ants walk around, he just goes across the tape to the next side, and he doesn't ever fall off. Also, if you could stretch the paper and connect the two circles, now you got a torus. So a torus is another example of a manifold. This one is known as, well, hyperbolic figure eight knot has the smallest hyperbolic complement. It's the smallest volume you can create and then have a manifold, a closed, simple structure. So I'll pass this around. Try not to squeeze it too much. It's kind of fragile, but take a look at the structure inside, the best we could do.
Hey, Pad.
Yeah.
I want to make sure that we have time for questions.
Okay.
So how?
I think we're getting real close to
Okay.
Yep. Maybe 5 or 10 minutes. Yeah. All right. So I'll kind of skip these. The 5 bases, the big main point is that there are bases we discovered in our measurements of the constants in nature and trying to put together the logic with going on. We've also discovered those derived bases and composite bases. Let me say what I mean by that. Derived bases are these: the megahertz, the femtometer, the electron volt, the mega electron volt, and the giga electron volt. And if you look, there's something strikingly showing up in the relationship between these numbers. They're all made out of zeros and a 1. And the offset in zeros is different. We can get relationships between them to make matches, but they're all 1s and 0s. This is a base 10 relationship between these things. Composite units are just to use the base units, the Coulomb, the second, meter, kilogram, Kelvin, and put them together more to 1 at a time. So Coulomb over seconds is an ampere. So that's a composite unit. So the thing to keep in mind that they all have factors of 1. It's not 2.36 Coulomb divided by 9.72 seconds. It's 1 Coulomb and 1 second makes it a composite unit. So, excuse me. Actually, let's take a break now, and then, yeah, it's a good time for that.
That was excellent. Thank you so much. I really think that it's, the way that you open the conversation, which is that this is a project that we ourselves are deeply interested in, I think is very accurate. That understanding how all of these things fit together is the only thing that will give us a complete picture of nature. And so let's take a little break, and then
let's take a short break this time because I really want to make sure we have time to discuss this a bit. And so if we can just take 5 minutes, that way we can talk for a bit before the eclipse and before lunch. Yeah. So thank you so much. Let's just get back to it.
All right. Well, what I was going to do here is take us to Wolfram Alpha to show everybody the search process. But since, maybe I'll leave that for questions if someone wants to. And just say, after doing that the first time, in fact, Avi suggested I do this for the Planck time, and then just do the search and ask the audience, which closed form would you pick? Out of all the given options that fit the data, which one do you think is the simplest, most beautiful? I'm pretty sure you would have picked this one. And why this is important? Because when we're trying to make sense of the Planck or the constants of nature, the first thing we discover right away is that the Planck constants are built into them. The Planck constants are only known to 5 significant digits. And as you saw, most of the constants of nature go out past that, right? 14 is the maximum. So in order to make sense geometrically of the connections between the Planck constants, you need to know the Planck constants in more than 5 significant digits. So we are making a guess that these things are all hyperbolic closed forms made out of hyperbolic actions. And this one, the exclamation point red n actually stands for derangements of 5 things here. Red n is 5. So then it just represents the number 44. But this is the construction that gives us how we partition the Planck boundary. And when we do that, we get this constant, this rotation 0, e to the rotation 0. And that rotation gives us the string of digits for the Planck constant, but it gives us more than the 5. It gives us the right 5 that we have known from the Planck time, but it gives us as many more as we want because you see we have a geometric construction for it. And then now I will switch to, don't get intimidated by this part. I've saved it for the end. Remember we had all those puzzle pieces? There's 288 constants in nature that we have to put together. Well, here we have fit them all together into one poster that has 288 features. Okay. But what I want you to notice.
This is the mathematical equivalent of one of those metabolism diagrams.
Yeah, kind of. What I want you to notice is whether or not you see a pattern at all. That's the question. That the valuable thing, how do I move this? I'm not. It really doesn't like me when I do that. Okay, zoom in. I can't get this thing to scroll up. There we go. Okay, so we'll start here. So the speed of light is underneath the title here. Speed of light made out of the Planck length divided by the Planck time. And all of these, first of all, are going to be two-part pieces, an external expression and an internal expression that fit in together on a double cover manifold. The internal expression involves the Giesecke constant, the one that's responsible for once you times it by 2, you get the hyperbolic figure 8 knot, and these two sets of j's. Let me zoom over here real quick. Oh, let's look for a pattern and see if you see a pattern here. The speed of light, constant below it. I hope you see a connection. And then the next one's slightly different, but then we see a whole series of ones that are similar. Okay, the big goal here is to find any pattern in the constants of nature, and the next step is to interpret the pattern. Okay, let's keep going down. The atomic unit of mass, a whole bunch of other constants, all depending on the right-hand side of 1 over the lemniscate constant, and they're all being made out of the same set of J1 minus J2. Now, this is just this column here in the poster. They're all J1s, J2s, all the way to the bottom. The sets of J's that we make, these are 3 sets of J's, are the ones that are, here's squares, 2 of them, and here's 3 sets squares. These are all from our equation right here. We said before, we have 4 J's together make 2 pi, sum together to make 0, and the quadrants of them make negative 4 pi. That's the collection of all 4 together. And if you want partial expressions, then you need to take collections of that construction that still give us one-dimensional outputs. So remember how J3 and J4 are 2-dimensional? You can combine them, since they're conjugates of each other, to get a one-dimensional expression, but you can't combine everything. You can't take any subset you want of these in order to get a one-dimensional expression. So every subset of these 3 equations that you can get defines the right-hand side of each column. See, all right, let's go right here. Here's a whole column. Hopefully you see a pattern between that bunch of constants in nature. Now, I should really heavily stress, compared to loop quantum gravity, string theory, any of the modern theories of physics, what they say, how they derive the constants, is completely blank still. There is no prediction for any theory. Okay? Our goal is to put all of these patterns together and recognize what it's telling us geometrically, and hopefully then see the picture of what the atomic structure looks like. Keep going up. Here's another bunch of constants that are very, very... In fact, you might notice if you know much about the primes, the 6 over E Euler-Mascheroni constant is a constant stuck in the prime construction. It makes it really, really interesting. All of these are very, very similar. What changes? We have, on the top one, we have electron mass divided by the Planck charge and the Planck mass. The next one's the proton mass divided by Planck charge and Planck mass. Then the neutron, then the muon, then the tau. That's all that changes in every expression. The right hand's the same, the left hand's the same, and just the mass of the top is different. All right, so we're not going to go into the details of this right now. You can ask questions, but I'm hoping that even at this point, you guys can see that there's a pattern being revealed in the constants of nature. And this pattern is all directly related to that hyperbola, the hyperbolic structure that gave us the answer for the fine structure constant. I'm not going to stand here and say that we understand it all completely. This is basically where we're at right now. Our understanding is that what we're really looking at is a hyperbolic figure 8 knot structure, and all the partial boundaries of the internal structure are these partial expressions here. To be seen whether or not we're correct. The exciting part is that we've found a pattern. We see connections now between constants in nature that before were measured completely independently. There was no pattern between them. What do we do with this pattern? And that's the next stage we're at. So that's what we do at the Physics Monastery. We spend all of our time trying to interpret these things and recheck them. I should be clear, we've got 6 that aren't on the poster because I've got answers for them, the best closed forms I could find from Wolfram Alpha, but they don't group up with other patterns, so I didn't include them because they would just look confusing. Hopefully, we find a better way to ask and find some better thing in the future for those 6. But out of the 288, we're missing 6, which is fantastic. It's a great place to be. Another really cool thing to point out, here's the Planck constants now, using the full geometric sets of numbers. The black digits are the known ones, and the green digits are the extended ones from the closed forms we're using, okay? And the things to notice, we got strings of digits, but you got powers with different numbers. 44 for time, 35 for length, 18 for charge, 8 for mass, and 32 for temperature. Now, in the structure of the periodic table of elements, which I hope is familiar to everybody. This is the most common periodic table. There's many ways to list it together, but this is what you get on Wikipedia. We have two things in the top row, hydrogen and helium. Okay, my best guess at this point is that the hydrogen atom represents the Giesecke manifold, and the helium atom represents the double coverlet, which is the hyperbolic figure 8 knot. And the internal structure of just those come with the Planck constants. And if you remembered in the last slide, let's look at the Planck chart. Let's start with Planck mass. It has 8 degrees of freedom. Planck charge is 18, and Planck temperature has 32. And other than the top row, the next 2 rows have 8 elements in it. And the 2 below that have 18 in it. And the bottom 2, if you take this bunch and put them in the picture, have 32 each. So I think the Planck division structure literally is showing us the entire chemical relationship, sets of chemical relationships. I think there's a lot more to explore here that are going to help us make sense of all the transforms available by the boundaries made just to make the simplest possible manifold. So that's where we're going. I'll leave just the speed of light here up as one I'm super excited about because it directly relates to that minimal manifold, right? The maximal possible speed related to the minimal possible volume complement or the minimal manifold. And here's another picture of the one I sent around. Let me make a video version of it. The stripes here are cutouts so that you can see inside. It's not part of the shape, okay? So the shape itself folds and closes completely on itself. We have cutouts so that you can see inside. If you were trapped inside or outside, you would stay stuck on either one. All right, and if you want to help continue following this conversation, I got a YouTube channel where I'm updating our best understanding. And I don't always agree with myself in the past, because if I find new information, I'll update that, okay? So don't expect that I'm speaking as an authority who knows what he's doing exactly right, or that knows that he's doing it right. I'm willing to change my mind anytime I get something that fits things better. But I think we have got fantastic stage. We've got great graphics. You might enjoy following the conversation if you like the talk today. And anyway, thank you guys. Also, thank you to CODATA and NIST for all the information that we're using to do all this. And Wolfram Alpha is our main power horse. I mean, I don't know if you've used Wolfram Alpha before, but it really makes a difference to be able to ask a mathematical question. If you can form a clear math question, but you have no idea what the answer is, go to Wolfram Alpha, okay? That's the best place to go. Maybe if you already know the answer, you don't need to. You can look up any other thing. But that's the place to go. And it won't just show you possible closed forms for the thing you're looking for. It'll give you all kinds of mathematical things that are connected to the same definitions. So it's like falling down a wiki hole, but it's a Wolfram hole. Yeah. And thank the Demystify Psi people for having this conference. It's been really fun.
Excellent. Thank you.
Nice. Sure.
All right. So, Shiloh, do you want to ask some questions, or should we go to audience questions? Okay, let's get some audience questions. So, folks, if you have questions, come on up. We have a microphone that is available. Any takers? All right, we got Ed Riffle coming. We got Zarin. Okay, these will be good.
Bye, buddy.
Did I take them?
Thank you.
I just have a real quick question. In your diagram, you showed one of the diagrams, your gravity diagram, where you showed the effect of gravity in 3 dimensions. I was kind of curious, have you modified that with the diagrams that they now show, where they have the sun falling through space toward whatever great attractor or whatever,
and all the planets are spiraling around it. Yeah, that's really just a change of perspective, right? You're just changing your reference frame, so now the sun looks like it's moving, and the same picture will have the same.
Except that what you've been saying is a lot about how physics work at any given time and place and space, and our time and place and space is always changing in a spiral to somewhere. I don't know exactly where.
Well, maybe I can extend that. So it looks like there's a vortex structure or this hyperbolic figure 8 knot structure. Where's the? Yeah, grab that from me real quick. Thanks. This, of course, is not to scale. And also remember, these cutouts are just to be able to see inside. But what I'm thinking is that when you make a hydrogen atom, that you're really making something that breaks up in 5 different ways. And each of those ways we associate with a different dimension. But the logic of each of those ways is bound together to the other 4. Okay? And the largest projection is the temperature projection. So the temperature is the one that's this outside boundary we're seeing. And inside, the things that are wrapping up are the mass boundary, this cone-on-cone structure that's being wound would be the charge boundary, and so on. So
what does temperature mean when you say
temperature, I mean to be a geometric part of the full set. So here, the outer boundary of the whole set that's subsumed by the internal construction would be the temperature regime. Yeah. It's a little difficult to try to transition temperature or even time as having geometric aspects, but this is what I think we're uncovering, is that all those things are bound under geometric rules, and they're actually making geometric shapes together. And if you understand all 5 together, you get a clearer picture.
I think of temperature, maybe it's old school, just motion of molecules and atoms in space, time. And we measure temperature kind of as a property that's
sure
wide scale.
Sure. But I mean it as in the dimensional sense. Well, let's start with this. If we have a projection of any kind, if it's something that forms a balance and it's projected, okay, then there's going to be an outer reach, unless you think it's an infinite projection. If it's finite, there's going to be an outer reach. There's going to be boundaries on the inside that determine how you're breaking this thing up and fitting the pieces to break up together, especially if it's a manifold, because there won't be any gaps between them. Temperature then for a single helium atom would be the largest scaled piece of the breaking up structure. Also then, therefore, the most shallow construction of its, bound, but it's the largest scale piece. So yeah, it's a physical dimension that's a little different to think of, but it also applies directly to when you have many of these things together, then you can get molecular action that have a describable temperature. They also have other describable features, but yeah.
I'm sorry. You take it down to a helium atom, a property which is a property of multiple things. I mean, we measure temperature by measuring the motion of molecules and atoms in a given space at a given time. Generally in a certain volume as well, because temperature and volume seem to be somewhat related to the old laws. Anyway, so when you say a single, how are you talking about vibration, rotation, but not motion through space?
Good, yeah. I'm talking about when we have a single geometric form representing a single helium atom. That's the simplest possible universe that can self-maintain itself. So it's a closed form. But that universe can be thought of projectively as having a 1. Its balance point is 1, and that 1 is broken up. It's divided up in 5 different ways. And each of the ways that the 1 divides define bases, and we label them time, space, charge, mass, and temperature. So it's, yeah.
I mean, if I can clarify it a little bit, I think the confusion might be that this is not a spatial entity, right? What you have, this is a representation of the articulation. You're using geometric algebras to relate the different properties of this structure. Yeah. So it's not a structure in the material sense. It's a relational representation that's not spatial. I think that's where the confusion is coming from.
Mm-hmm.
Hello. What do you think of Rupert Sheldrake's story going to talk to somebody at NIST about whether the speed of light changes, and that it does experimentally seem to change until the length of the meter was defined by the speed of light, therefore getting rid of this problem that experimentally the speed of light changes when measured by a meter and a second that are defined not by the speed of light?
Well, I should say I'm open to these things being changeable, but right now the common understanding is the constants in nature are fixed features of reality. People will argue over time, does that change? It's possible. If that were the case, then the model by which everything is balanced together should be changed in its shape too. I'm currently in the camp that I think these constants are fixed features of logic. Of course, experimentally, the speed of light in a vacuum is different from the speed of light in a crystal or a speed of light in air and so on, right? So it can experimentally change in that sense. But yeah, I'm open to all possibilities. right now I'm working mostly off of the NIST CODATA data set and trying to explain their connections. So that set is assumed that these are all fixed features.
I would just like to introduce an interesting concept with the torus that you've got in your hand, that can fractal all the way up from subatomic particles all the way up to the whole universe. That's the fractal process. If you see it as a torus around the sun, and you're thinking of the sun falling, which you've just been describing, and it pulls the planets along behind it, those planets are sitting in that vortex in the hole in the middle and falling with the sun. But if you've got a set of planets sitting in the hole in the middle, you've got a second set of planets sitting in the hole underneath. They can't be falling with the sun because it's going the wrong way. So what we've introduced is the concept that if you put the sun into reverse time, it's falling up and it's pulling those planets up with it. So you've got planets going down and planets going up. Can only work when you've got time and reverse time. This is just a fascinating concept because then you get a balance between the two, and it introduces a whole extra solar system of planets on the other side of our sun.
On the other side, like on the inside, or the other side in hidden bees?
They're hidden behind the sun because they're in that bottom vortex. We can't see them because the sun is always in the way.
Well, wouldn't our spacecraft see them when they go around?
The spacecraft are spinning in the same vortex. They don't actually get all the way around.
Trapped in that,
they're trapped in that vortex.
I'm particularly very sympathetic to the notion that the structure we're after is fractally constructed.
Absolutely.
There's a fractal nature to it. In fact, the charge boundary, the simple closed form we found for the charge boundary, like the Planck charge, has the Weierstrass constant dead smack right in the middle of it, which may know as known as the simplest fractal. So, yeah, that's what I want to say.
Just Kim. My question is, first of all, I've dealt with the concept of energy all my professional life for electric power.
Is the mic working?
Yeah.
Okay.
I've always dealt with from a professional point of view with energy, as I've delved into these topics, I don't understand what energy is at a fundamental level. And since you're talking about the constants of nature, is there a constant of nature associated with energy specifically that you've been dealing with?
Javi, can you go to one of the columns, the energy column on the constants of nature poster? Yeah, so ask that last part again. Say the last part again, please.
Are there constants of nature that are related to energy?
Yes.
And what energy, that gives some insight as to what energy actually is, since it
Yes.
seems to drive everything.
In fact, maybe the best column in our whole poster right now. Let's see, go to left. Keep left. That one. To the right-hand side and then blow up. The furthest on the right one.
Okay. Right.
Other way.
Up, right. Well, not right. So
Keep going. One more.
yeah.
All right. Now, maybe zoom out just a little so we can get the first 8 in there all at once. This entire column seems, well, first of all, there's a giant pattern, but the first 4 on the right-hand side are made out of half real imaginary power towers. So I to the 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 I, which you can imagine twist, rotation, 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 but always a new orthogonal rotation. And the next 4, so the 4 half reals and 4 half imaginary, fitting together, and the signature, the signs are 3 positive and 1 negative, and 3 negative and 1 positive. It looks like this is the 4-dimensional hyperbolic central structure, but looking right down the throat, where things are rotated on and fit together. Now, if we zoom down on the same column, you notice that these are all energy expressions: E sub n, E sub mu, E sub tau, E sub he, E sub d. These are all constants of nature, the energy of the triton, energy of the alpha particle, and so on. So they've got an extreme perfect match. Out of all the columns, this is the one with the simplest set, going all the way to the bottom. So all 36 of them. And they're all descriptions of the energy content in the constants of nature. Exactly what that means, well, I've kind of given you my vague impression. we're looking, this column looks symmetry-wise right down the axis of how things fit together. But it's really interesting that the thing that fits them together scale by scale is this eye to the eye rotation all the way down. So yeah, that's what I can say for now.
Thank you very much for your explanation, and I'll investigate this a little closer. Thanks.
Cool.
Hi.
Hi.
Hey,
By the
I
way,
guess
I can't believe you have a fear of public speaking. You have a fantastic voice for public speaking.
A voice made for radio.
Yeah.
all right. So I guess my only question right now, because I don't know much mathematics, so like this is just like I have to like understand a lot more before I can actually like look at this and understand what I'm looking at. But anyway, I did have a question about because I feel like I've always heard like suspicions, rumors, whispers about the gravitational constant not necessarily being the most constant thing. I was just wondering if you had any sort of perspective on that, and I just wanted to hear what you had to say.
Sure. I think the gravitational constant is a fixed thing. Of course, I can change my mind in the future. That's what I think right now. But that's because it fits so well back into this set. And when the whole pattern lumps up, it's starting to tell us something more. So if it were to change, we'd be breaking that whole column, the symmetry in the whole column. So that's my reason, is just for the symmetries we're finding. But it is a conversation in science right now whether or not the constants do change over time, right? But there's another question whether they change through scale. So if you make a measurement on a larger scale, would the constant slightly change, like the running of the masses and so on? But so it's a very interesting question to keep in mind. But I think currently that gravitational constant is a fixed constant.
Thank you.
I think
So you have digits that extend beyond the known digits. Did you have any opportunity to validate some of your predictions?
Yes, we've got 2 more confirmed predictions in string theory at this point, huh? We've found forms, and then since we found those forms, they came out with new updated measurements that matched even better to the number we were having. And so you can call that a verified prediction if you want. What else did you ask?
factoring.
Yeah, and the G factor was one. Yeah. But now, as you can see, well, I haven't shown you the numbers that get spit out of this, but I hope if you know what the each input is, you can go to Wolfram Alpha and plug in the number for the Planck length, plug in the number for the alpha particle mass, plug in the numbers for the Planck time, and then multiply by 1 minus the number for the imaginary part of the infinite power tau of I times by J r squared. By the way, J r squared is, we have J r and J theta, which are just the radial expressions of J3 and 4 versus the Cartesian expressions. So we have J3 was a 2-part number, a real and an imaginary part, so X and Y parts. But you can think of that in a radial sense also. So that's what J r is. It's also J r squared is equal to J3 times J4. Okay. Anyway, on the legend on the far right-hand side, we're going to make this poster publicly available. And I do update things over time. We have updated this thousands of times, so don't expect there won't be changes. But the ones that have the most symmetry or the least likely to be changed in the future, the legend on the right-hand side gives you the names of everything on the poster and gives you the first 15 significant digits. We can't verify anything past 14 because there are no constants of nature that have measurements past that. But so this should be enough information to look everything up and plug it in and check it for yourself. And yeah, hopefully some of those constants, if you are mathematician or mathematically inclined, you're already familiar with many of them because they are the central, most beautiful constants in math and geometry. So,
Excellent. I like that it's verifiable and open to exploration like that. Do we have more? Oh, we do have more questions. I'm sorry, Solomon.
Thanks for the very interesting talk. I was at some point in the talk, you were kind of, I'll say, I find the constants that are dimensionless to be the most compelling because it feels like the scale is not in any sense arbitrary. But it felt like you were claiming that sort of there's some really intrinsic, meaningful thing behind the units that we use, meters and seconds and things like that. I always felt like this was just sort of an arbitrary scale. Maybe you can, come up with a nice, like very precise definition, but we could have just as well have had the basic unit of time be, half a second or 3 seconds or something like that.
Great question. Thank you. So I am saying that they're not arbitrary, but I completely understand thinking that. In fact, I thought that most of my upbringing in physics. I don't think it's common for physicists to have looked at these constants of nature, to have even seen the names of many of them, dozens of them are just kilogram Kelvin relationship or the meter kilogram relationship and so on, right? Those bases are uncovered from these fixed actions in nature. We find them from there. But what that means is that when we have equations that each constant belongs to, that we can use that equation synonymously with other physics equations without changing our system. So when you take the whole set of equations, and when you take any one equation that say only has 2 dimensions in it, it's not so obvious that those bases are the fixed bases. When you take all the set of equations, then those fixed bases become really obvious, because if you put all the equations that the constants show up in and then change one base, you see that dozens of equations become more complicated all of a sudden. So our goal is to get the simplest possible expressions, and in that quest we've uncovered there are bases that make it possible to give us the simplest expressions in the equations themselves. So yeah, I am saying that the 5 bases are inherently part of the logic built into atomic matter, and one of the big mysteries we're after is to understand why exactly those bases, how do those bases fit together, why are they responsible for the logic of all the actual expressions that matter can hold or have.
It's
I'd coming back for a second one.
you just real quick. Are you in contact with NIST about anybody in NIST about this?
Not yet.
View?
Not yet.
Not yet.
I've still spent all my time. I'm not convinced that we're all the way at the end, because the more things group up, the more I get confident, but I'm expecting everything to be all grouped up perfectly at the end. And we still have 6 that we haven't answered. I'm sure there will be communications with them in the future. Not yet. I spend all my day focused on each question. So I do very little outside communication. So that's probably why.
Which is that we're using their as the basis for your work. And I was wondering, the people at NIST, the people at NIST are always working on these, and I don't know whether they actually have a channel for that data to be flowing to you if anything changes.
I hope there's somebody at NIST who's working on trying to figure out the pattern in there. I think really their job is to report the best measurements and read the recent papers that come out and adjust the numbers based on the best measurements. That's really where I see their focus so far. But hopefully there are people there, since they have access and directly work with the numbers, who are directly trying to make sense of it too. I think they would be very interested, yeah.
Well, I can't help but notice the number of dimensions is 5 there. Have you done like any perturbation in testing on your, break and scale symmetry? If you could explain that, I didn't quite grasp the break and scale symmetry either.
All right. Well, imagine you make a system, but the most fundamental thing you want out of the system is that it's self-perpetual. Okay, so you're going to need the system to have its ingredients, and its most base ingredient, to close some loop. So if you form a circle of any size, then that's your basic ingredient by which to build things that are larger than that. So circles happen to have this amazing feature that if you have one circle and you're building more circles on top of that, so you surround a circle with more circles, it's exactly 6 circles outside that will kiss all together and form the next largest scale. You can imagine a ring around all 6 of them now to get the largest new sized circle built from the smaller circles. So that second sized circle, compared to the first sized circle, is 1 to 7. You get exactly 7, so 6 with 1 on the inside. Okay, and so that's a break and scale symmetry that comes from circles themselves. It's a factor of 7. So the blue B right here is a factor of 7 for the break and scale symmetry, exactly for that reason. So we think at the bottom construction, we actually got, in fact, you can kind of see, imagine in here, if you draw a circle around the figure 8 knot in the middle, the size of that circle, then copy it, you can fit 1, 2, 3, 4, 5, 6 more inside there to get out to this scale. Anyway, yeah.
That would be in a 3D space. It sounds like a packing problem. Now, is n related to b? Like if n goes up, does b go up?
Well, I think those are fixed in this picture, but yeah, it would.
I think I've got the hardest question for you to answer. Do you answer your email?
Yes, I do, if they're polite.
The reason I say that is, I attend a lot of conferences, and the hardest thing for us to do oftentimes is there's a lot of questions and a lot of ideas and concepts we would like to share or get your perspective on, and you never have the time to really explore because everybody's got a lot of work to do and other things like that. So what I've always wondered is people's work processes. If people want to send other researchers and things like that, how do we limit our time? How do you work? Because when I was talking to Pierre, like, how do you work, and other scientists, and we just don't have a lot of space to answer questions. And have you found a collaborative method that you're working with that somehow could tie people in without the cacophony that occurs, out there?
Yeah, I understand.
And so I think that's the hard question. How do we really collaborate and share ideas? And I would like to know what your process looks like, how you reach out, how we can reach out to other people, because as I was talking to other scientists, there's a lot of stuff going on, and yet we just seem to be working in isolated pockets. So I think that's one of the hardest questions we have to answer as research scientists, et cetera. How do we actually effectively come together so that we can look at the holistic ideas that are forming planet-wide?
Yeah, that's a great question. And also, I would add that I think it depends on the field you're researching. There are some fields that are quite actively full of positive collaboration. And there are other fields, as we saw yesterday, that have very been stymied in even talking about it, right? It's very difficult to publish a paper on something about fundamental constants in nature. There are no working physicists working on that. There's nobody with a PhD that would actively proclaim, this is what I'm doing, and for fear of losing their job. So it's a difficult thing to move forward with. There's a difficult place to find where there's a conversation where people are trying to do that, since all the pressure is not to, right? So me personally, I got one point, I didn't think I was going to survive much longer. I thought I had to the end of the month till I couldn't pay rent and couldn't eat. And I'd lived a really good life, done a lot of good things. And I thought, all right, I am not going to respond to this crisis by trying to worry about the money. I'm not going to do that again. I've done that before, and some of my biggest regrets have come from worrying about the money and responding that way. What I want to do is understand one new thing about physics before I die. If I devote the rest of the month, every waking moment, sleep 8.5 hours, because that's what works best for me. I feel refreshed all the way. Wake up, and the moment I'm awake, I'm thinking about this mystery, and I give every thought. That's the maximum I can do. And I knew I'd never actually done that. I'd read physics books for decades. I'd really worked for hours a day, but I'd never given every thought of the day. And I wanted to feel like I had done that. Now I'm kind of in the practice. This is the first time we've gone away for a trip as the Physics Monastery. However, we have other people at the Physics Monastery have completely different methods. They spend all day too, but like Matthew is usually our coordinator for outside contacts and reaching people. So yeah, we do encourage talking to people about these ideas. We encourage the world to get more full of people who are individually trying to make sense of these mysteries. Because the goal is not for some smart person in the world to figure it out for you and tell you what the story is. The goal is for you to understand a story that makes sense of it for you, not just that someone else did, right? So we need a lot more people asking the questions that are fundamental. And I know it's scary because you're likely to be wrong the whole way, right? You're likely to never even make it right. But if we discourage people for that reason, then we'll never get there. So I respond to emails, but it might not be right away. It might be several days lag. We also try to hold conferences at the Physics Monastery every now and then. So people are welcome to come. I prefer in person to those meetings because I find the online stuff very distracting. And usually we don't get to the depth of the conversation I'm interested in. But people are welcome to come participate for free in these conferences. Sometimes we have people camping out, sleeping on the floor to have enough room for people, or people get nearby hotel rooms, whatever it takes. But for me, I don't see a lot of professionals that have spent 20 years learning physics and teaching physics working on this. So that's not a pre-qualification for me. Being a human with consciousness that's identified this as important is more important. Anyone's welcome to try. I mean, that said, I'm not looking to entertain all my day looking at all kinds of crazy ideas. I want people who have really thought things through or want to think things through and are very serious. But that could come from any walk of life.
Fine, all right. Thank you all for the questions. And now, Shiloh.
Yeah, I'd love to get have you spoken with Alexander Unzicker about this epic
I've followed his stuff
journey
for years, and I think he was one of the first people I saw really proclaiming to other physicists in the crowd that we need to get back to doing this, because otherwise we're not doing real fundamental physics. We teach all the undergraduate physicists that this is the goal, and then we don't let any PhDs work on it. Yeah, he's been saying this for maybe a decade now. I can't remember how long it's been that I've seen some of the videos. I haven't directly talked to him yet, but I strongly suspect that he'd be very interested.
Yeah, maybe we can get you guys together for a conversation in the near future, because I know he's also obsessed with really computing. He wants to be able to compute very similarly. Another just comment that I thought that I might make is that I think that the approach of setting up these tables and finding patterns has a rich history that I'm not sure, maybe you're probably aware of, but when I was studying how Newton came up with calculus, he did it very similarly to this, right? He made a table of relationships between the rate of change, and he saw the variables fall out. You can actually see it if you look at these tables. You're like, oh, well, you just move the exponent down. Like, it makes perfect sense.
Yep.
And so it seems like a very a rich history of using this method to deduce simplified patterns.
And in general, this is how science works. We look for patterns. You might not understand the pattern at all when you find it, but then we try to make sense. The pattern gives you clues of what else to look for, what else to ask, and so on. So yeah, I think it is. It can be very daunting because these patterns show up in terms of equations, in terms of things that might be all Greek. But if you're willing to put in the time, I'm pretty convinced. I've tried to make it as clear as possible in there. We have everything included on the legend. All those things you can look up on Wolfram Alpha or Wikipedia. They're not unknown things, right? We're not making up any new constants to make sense of the stuff. Maybe we need to. Maybe the 6 that are missing are still some other concept that's not discovered in math or geometry yet. I mean, that's certainly possible since our history didn't start out knowing them all. But yeah, I think it's accessible if you're willing to put in the time. It's difficult to penetrate because of the format being equations, but that's the best I can do at this point.
You started out the conversation by saying, by setting up this idea that if we were able to see the world differently, we would be able to move forward and change the world that we inhabit. And I wonder if you have a sense of what that change is.
Absolutely. I really do. I'm a big fan of Star Trek.
Okay.
Conceptual model of the future where there isn't money, or money isn't the main mode by which we all focus and our security comes from and so on. I think it's too easy to manipulate people and make them slaves of a system or a group of people when you can't even get food without the money. What I'm seeing ultimately is that when we understand the atomic structure of matter, it should, and I hope in my lifetime, but it might be 1,000 years away, enable us to make in place, in situ replication, where we can make anything that's makeable out of atoms on purpose because we know the internal structure. And ultimately, it'd be really sweet if you took as an input nitrogen gas. Things that have mass boundaries can be twisted and formed into anything else, into any other arrangement of mass boundaries. So I'm seeing a future in which all humans are elevated at a different level, where all the resource needs are only dependent on their understanding of the resource needs.
And so when you think about something like the attempts to gain fusion that's actually productive in producing more energy that it consumes, do you find that our difficulties of being able to achieve that are related to a lack of understanding of the stuff that's in your table of constants?
Yeah.
And so you think that they're just barking up the wrong tree? Do you have a specific
I think they're
way?
barking up the best tree that they know how to.
Sure.
Yeah. And what we're missing is a fundamental picture. I mean, most people are told that it's random. The quantum mechanics is indeterministic. There is no structure defined there. I think that's absolutely wrong. But I mean, yeah, I think once we do find the structure, it'll allow us to then uncover the alphabet of nature and just then construct the words and sentences and so on, which will mean it'll allow us to start thinking in terms of that alphabet. We don't do that at all right now. I don't do that at all right now. But when we get there, we will think on a different level. And the things that we think are impossible right now could be incredibly easy. I mean, in the past, this has already happened many times. We use electricity and are dependent on all these things that use electricity now. But in the past, no one even heard or thought of an electron, right? They were around them all the time, but they couldn't conceive of it or conceive of how to take advantage of it. I think there's a whole other threshold, or many other thresholds for us to cross, which we're taking advantage of internal structure of the atomic material around us in completely new ways, like making our own dinner. And I really look forward to a phase of life where when we meet people, the thing we get to exchange instead of a power hierarchy or try to have some sort of, a way we're going to be making money off of them. Instead, they might share with us the favorite meal they've ever found in their whole lives. And you save it in your phone. And anytime you want to eat that meal, you just use your replicator to make that meal. I mean, that changes the dynamics of humanity a lot. And it changes what we focus on. And I think once we free ourselves up from needing to survive, the things that we can accomplish together are really going to amplify.
I'm very sympathetic to that because I do feel like the idea of post-scarcity is kind of what drives a lot of science and a lot of innovation. People that are passionate about the future tend to be passionate about the idea that we are moving towards something that is more equitable and fair than the society that we live in. But if I look at a transition that's happened in the past, like with electricity, I'm struck by how little of an understanding we needed to make that transition. And so do you think that there's
Good
something
point.
categorically different about the time that we are in today that we need to have more knowledge to make that transition? Or is it something else?
I think we're more likely able to make that transition today. We have tools that allow us to put together a larger data set and try to make sense of it. We have tools that can do things that we couldn't do before. And those things then help us understand them in at least partial ways. And I think as we approach a picture that makes sense of this whole mystery, that the biggest transition that will come is we'll understand the mystery. It'll be a conversation in grade school to high school about physics and chemistry and biology. And those will all be kind of a continuous conversation without questions that we can't answer about why those features exist. This is what I'm imagining, at least. Now, I can't predict exactly how long this is going to take. I just know it's worth the effort to get there.
With the rise of AI and your own use of these computational tools, do you have a sense that there's a displacement of the effort onto the human minds, from the human minds onto the machine minds? Where basically, because you're saying that, okay, so we need to be able to see the complexity of the interactions. And the complexity of interactions that you're seeing in a large part comes from Wolfram Alpha, which is this computational tool that allows you to sort of to just chug the raw numbers into each other to see the relationships that come out. And so is the transition necessitated by the computational developments that are occurring? Could it happen without AI systems?
I think it can or could happen without AI systems. And I do see that the AI systems are also getting some people to think less, right? The Wolfram tool, I wouldn't include in that group. It doesn't just give you closed forms. It'll also, you can ask any question about an equation in calculus. And then all of a sudden you'll have a whole list of related things that allow you to explore more and make more connections and therefore come away with way more understanding than you were asking for about that equation in calculus. So that said, I also think currently we've come up with a lot of other systems to distract people from thinking more, right? The first one where we're all focused on money, but also, I mean, how many people spend once in the entire year thinking all day on purpose instead of letting the outside world distract them, take their attention, right? How many people are in charge of controlling their attention for what they're after instead of looking for things that will entertain them or take their attention? I think it's gone very far one way. And I think many people have kind of maybe lost track of the joy of getting to think all day, or the joy of walking for 8 hours with no interruption, with no music, under thought. Now, Einstein used to do this a lot. He said there was something magical about walking and thinking. The walking process helped you think more. You come up with new insights. And I hope everyone remembers how delightful it is to come up with an idea that changes your world personally, that makes you think differently from then on about a whole bunch of things that you regularly think about. That's extremely delightful. And I might call it the process of growing up. Today, we've kind of lost the aim of growing up because, well, how do I frame this? How do you know whether you're still growing up? Well, do you see the world the same way you saw it when you were 5? If the answer is yes, you haven't grown up since 5. Do you see the same world as yesterday? If the answer is no, then you're still growing up, right? So I think that process is extremely delightful. And we got very sidetracked with entertainment, with those who were taking our attention on purpose. If we get back to understanding the joy of being in charge of our own thought and not looking for entertainment, but instead looking for insights, then we can elevate ourselves. But also we encourage ourselves to continue the process the more we practice doing that.
Seems like that was that's the utopian dream of the academy, that you would be bestowed with this almost, I don't know, monastic ability to think all day. But it seems like, and I don't want to be disparaging about the future, because I think that the rise of independent institutions like your own are perhaps the solution set to that, in so much as you can provide people a space to be able to do that. Do you have a sense that that kind of alternative structure is proliferating in the world, or what? How do you see the future of inquiry in the best case scenario?
Oh, in the best case scenario, yes, it would be really nice to have that proliferate. I also think it'd be really important for everyone to remember this isn't just about sitting and thinking about what you can conjure. Whenever you're stuck, the best guide is nature. Look into nature, travel. Go see something you haven't seen. See natural things that you've never been exposed to. Touch them, taste them. Be in the world in a way that you haven't been, because if your guide is nature, you'll figure more out about nature.
Yeah, so maybe I want to kind of twist this back. So, there's this really interesting Feynman quote. Feynman? I'm not sure how you say it. Feynman? All right.
I say Feynman.
Sorry, Richard. So, you mentioned that he said that if we were to preserve one piece of information, it would be that the world is made out of atoms. And that rings really true to me, with the material science background. And, I think I guess I would modify it. And I think what he was getting at is that it's something more like all things are made out of bodies in some sense, something more general, a general form of that. And, you might call it whatever you will. I like the term fiber for these bodies because it implies the possibility of an irregularity or an inhomogeneity of the shape of these. And I noticed we're using spheres a lot to approximate these atoms, which is why I think that it's perhaps limited if we don't open it up. What do you think about the idea that there could be all sorts of diversity of form to these fundamental particle systems and so forth? Could it might not be such a symmetrically laid out universe?
Well, ultimately, all the asymmetry we see in the world are coming from these particles. So certainly there's asymmetric forms involved. I'm particularly interested in uncovering a non-reduced dimensional perspective of the Hopf vibration, which has a lot of fibering in it, right? It's a map between the 3D sphere and the 4D hypersphere. And I think that's a large part of the story we're after. Getting the visuals accurate and understanding it hasn't occurred for me yet, but that's one of our major projects at the Physics Monastery right now. So yeah, I think there's a lot of asymmetric structure going on. Also, what we're uncovering is a story that's suggesting that the universe isn't just hyperbolic, but hyperbolic structures are incredibly asymmetric in scale, right? Scale matters a lot in hyperbolic structures. So yeah, I'm very sympathetic to the idea of fibering things and asymmetries.
Yeah, and I think that the interesting part here in translation for me is that a lot of, like we mentioned, one of the first questions was regarding how you have created this relational map, which you use these geometric principles to draw this map out. And as a material scientist, I'm really just thinking in terms of 3D objects interacting with one another. And to that end, when I look at a physical equation for something in the material space, like we can take the most simplest form, like the Hookean deformation equation, right? You have a constant in there, and for each material, essentially, you have a modulus, right? And it might seem like a mystery at first, but if you look at enough materials, you start to realize that what this modulus is telling you is the relationship between the deformation and the amount of effort you need to put into deforming it. So when I look at these constants of nature, even the speed of light or something, I'm always thinking in terms of what is this saying about the material properties of that substrate itself. And I'm wondering if, as an example, the speed of light seems to suggest to me the rate of deformation of that substrate. Do you have any space in your mind for thinking about these physical constants in terms of what they would say about the material properties of the atoms that underlie them?
Yeah, absolutely. In fact, that's our main goal, is to understand those aspects of it. So I currently expect that we have a geometric form, whether I'm right about this one or not, and that the partial interactions that make up that form give us all the actual exchange relationships in nature and atomic structure. So yeah, absolutely.
And then I guess I have one last point. So somebody asked, what the hell is energy? And I can't think of a better definition for energy looking at all these equations than something moving somehow. What do you think about that?
And I think it's significant that you were saying that it's down the barrel of the torus where motion would be strongest.
Yeah. So energy moving somehow, but we're also usually interested in energy that's not exploding or contracting, right? Where stable energy forms.
A potential of some sort.
Yeah, I mean, we could use them to do explosions or contractions, but the forms we're interested with energy boundaries are things that are maintaining themselves. So I think that the Giesking manifold, in whatever all of its structure looks like, defines the minimal boundaries that you can wrap things around in a closed form. So I think energy and geometry are directly connected in that sense.
So before we break for lunch, I wanted to ask you, you made this point at the beginning about the confines of a flat world where there's a fear of exploration because you know that if you go too far, you might fall off the edge and you don't have the ability to pull back from it. And I wonder if you have a sense of where that fear of exploration lies today, because I don't think that the fear disappears. I think that it shifts position. We're no longer scared of falling off the edge of the earth, but surely we're scared
of other things. Yeah. We become less scared the more we personally practice to conquer the fears. When you go out to the things that you're afraid of and challenge it and find out it wasn't that scary, or discover the way to manage the thing that's scary, then maybe it's an eternal process of shifting the fear. Maybe that's part of being conscious. The things you don't understand intrinsically have something terrifying about them. But I also think that's the exciting part of life, is to face those terrifying things, to stare them down, and to figure them out.
That's where growth happens, eh?
That is where growth happens. But I wonder specifically, like there's the specific example of the sailors fearing the edge of the earth in the sense of exploration. And so in the sense of exploration today, do you think that there is a similar universal place of fear?
I think at least from my perspective, it seems that the thing that keeps people back from exploring is they don't know how to make money doing it, right? They don't know. And maybe there's a ridicule from, oh, you're wrong, you're a crazy person doing it because you're the only one doing that. So there's a lot of peer pressure fear that we're trapped in right now. That's what I pick up mostly. I think every human, though, intrinsically has that drive to want to figure it out. But maybe they've encased it in well, it's not worth it because I can't make money and no one's going to think I'm cool if I'm not making money doing it. Right. So that's what I pick up on.
Yeah, definitely. All right. Well, thank you so much. This is really wonderful. And
Thank you.
Yeah.